ଆସିଲା। ସାର୍ ଏବେ ଦେଖନ୍ତୁ ହଁ ପରେ 50 କି ହଉ ଟିକେ ରୁହ ଟିକେ ରୁହ। ହଁ କରୁଛି ଏବେ ଆଉ ଚାର୍ଟ ବକ୍ସରେ ପକାଉନୁ ସେତିକି ହଁ ଡିଲିଟ୍ କରନ୍ତୁ। यूट्यूब लिंक टा चैट बॉक्स रे दियंतु। यूट्यूब रो जो शेयरिंग लिंक टा हाँ हाँ सर आमे एबे चेक करिया पे दियंतु तापर देखियानी पठाया तो सबले अपडेट मारिया ना मो पाखरे सेमति ही थियो मु एपटे मझरे मझरे यूट्यूब लिंक पकोउथि आ सेटा चेक करिया सर टिके चेक कले ना ना सही लिंक रे ही अछि ठीक अछि सर वही सर ठीक अछि सही लिंक हो ताले एबे स्टॉप करजी ना चलथियो अरे स्ट्रीमिंग ओबेस टा चालू तो हो तो शेयरिंग करी मोर चलछि कि हो एटा एटा वाइड डिफरेंट नहीं पूरा फुल स्क्रीन आ छोट बड़ कहीं करिया से एतिकी फिक्स भलो अछि पूरा हला yes ତାଙ୍କୁ ଏବେ ଗଲା ତ boys are all set ହୁଁ ହୁଁ ହଁ ହଁ hello ଆଉ ସାର୍ ଗୋଟେ ଜିନିଷ ଏଇଟା ଯେହେତୁ ଏବେ ଲାଇଭ ଷ୍ଟାର୍ଟ ହେଇଗଲାଣି ଏବେ ଆଉ କିଛି ଖେଚଡା ବି ନାହିଁ ହେଲା ଆଉ ଆରାମରେ ଆପଣ ୱେବିନାର କରନ୍ତୁ ଠିକ ଅଛି ହୁଁ ବୁଝିଲ ସାର୍ ଓକେ ଭୋଇ ସାର୍ ଫ୍ୟାକଲ୍ଟି ଗ୍ରୁପରେ ବି ପକେଇ ଦିଅନ୍ତୁ ଆଉ ଥରେ ଆଜି ଗୋଟେ ପୁସ୍ କରିଦିଅନ୍ତୁ କାହିଁକି ଜଏନ୍ ଖାଲି ହଁ ଖାଲି ମିଟିଂ ହୁଁ ସସ୍ମିତା ମ୍ୟାଡ଼ାମ ଗୁଡ୍ ମର୍ଣ୍ଣିଂ ଗୁଡ୍ ମର୍ଣ୍ଣିଂ ମ୍ୟାମ୍ କେମିତି ଅଛନ୍ତି ଆଉ ଓହୋ ଆଚ୍ଛା ଆଚ୍ଛା ହଁ ହଁ ଓକେ ମ୍ୟାଡ଼ାମ ହଁ ଘରେ ମ୍ୟାଡ଼ାମ ଏଇ ଜଟଣୀରେ ଲକଡାଉନରେ ତ ଅଛି ଆଉ ହଉ ହଉ ମ୍ୟାଡ଼ାମ हेलो। हाँ साला कौन कर ये तो भाई मॉब। हाँ। अरे ये यूट्यूब लिंक भी चेक करो। ठीक ठीक ठाक आସୁଛି ନା ତ। ହଁ ମିନିଟ୍ ରହିବି ଯେ ମୁଁ ଟିକେ ମେଲ୍ କରିଦିଅ ମୁଁ ଆଜି। ହଁ ହଁ। ହୁଁ। ଏବେ କଣ ଦେଖା ହଉଛି? ମିଟର ଦେଖା ହଉଛି। ପର୍ଟିକୁଲାର। ହଁ 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 ସେଇ ୟୁଟ୍ୟୁବରେ ଚେକ୍ କରିବା ପାଇଁ କହୁଛି ନା। ଦେଖ ଠିକ ଠାକ ହଉଛି ନା ନାଇଁ ହଲିଲେ ମତେ କହିବ। ହୁଁ। କୋଉଠି ଓବିଏସରେ? ହଁ। ନା ନାଇଁ ସେ ସ୍କ୍ରିନ୍ ହିଁ ଚାଲୁଥିବ ଯେ ଓ ଏମିତି କି? ହଉ ତାହେଲେ ମୋବାଇଲରେ କରିବି ଆଉ। ହଁ 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 ହଁ। ହଁ 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 ଆରେ ଶୁଣ ଶୁଣ ଆଉ ଗୋଟେ ଜିନିଷ ମେନ୍ ହେଲା ଏମାନଙ୍କର ଟିକେ ଭଲଟେ ହେଇଯାଉଛି ଯେହେତୁ ଆମ ଉପରେ ଡିପେଣ୍ଡେଣ୍ଟ ଅଛନ୍ତି। ଆଉ ସେଇଟା ଭଲ ଷ୍ଟ୍ରିମିଂଟା ହେଇଯାଉ। ଆଉ କଣ ତ କହୁଥିଲି ପରେ ତ ଫିଡବ୍ୟାକ୍ ଆସିଲେ ମତେ ପଠେଇବନି କି ଧଡ଼ ଧଡ଼ କରିଦବ ଆଉ କଣ। ହଁ ହଁ ହୁଁ 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 ହଉ ଏବେ ହଁ ଠିକ୍ ଅଛି। ହଉ କି ସରି ସରି। କଣ କଣ ନାଉ ନାଉ। ହୁଁ ହୁଁ ଦେଖାଯାଉଛି। ହୁଁ 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 ହଁ ଏବେ ଟିକେ ଦେଖ ତାଙ୍କ ଭିତରେ କଣ ଚାଲିଛି। ହଁ ସ୍କ୍ରିନ୍ ଟା ଫୁଲ୍ ସ୍କ୍ରିନ୍ କରିବି ନା କଣ କରିବି? ଫୁଲ୍ ସ୍କ୍ରିନ୍ କରିଦେଇ ଚାର୍ଟ ଅଫ୍ କରିଦେଇଛି ଆଉ କଣ। ହୁଁ 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 ମୋତେ ଲିଙ୍କ୍ ପଠେଇ। ହ୍ୱାଟ୍ସଆପ୍ରେ ପଠାଅ। ହ୍ୟାଲୋ। ହଁ। ଏବେ ଆଉ କିଛି କରିହବନି ମ, ଷ୍ଟାର୍ଟ ହେଇଗଲାଣି, ପୁରା ଦେଖାଯିବ ତାଙ୍କୁ। ଥାଉ, ଥାଉ ଚାଲୁ। ଆମେ ଆମର ହଁ ଦିଟା ଯାକ ପଠେଇଦବ, ମଝିରେ ମଝିରେ କରିଥାଉ ଆଉ। ତାପରେ ମୋ ଭାଇର ମୋବାଇଲ ବି ଅଛି। ଗୋଟେ କୋଉଟା ଆମର ଇନାଗୁରେସନ ଏବେ ଚାଲିବ ସବୁଠି ହେଲା, 10:30 ପର୍ଯ୍ୟନ୍ତ ଖୁଚୁରୁ ମୁଚୁରୁ ହାଇ ହ୍ୟାଲୋ ନମସ୍କାର ହେଲା କି। ଏବେ ଦରକାର ନାହିଁ ଯେ, କିନ୍ତୁ ଲିଙ୍କ ଟା ଥାଉ, ଯେତେବେଳେ ଫ୍ରି ହେବି ସେତେବେଳେ ମୁଁ ପୋଷ୍ଟ କରିବି ନା। ଏମାନଙ୍କର କାହିଁ ପାର୍ଟିସିପେଣ୍ଟ ବଢୁଛନ୍ତି ଏବେ ଆସ୍ତେ ଆସ୍ତେ, 300 କେତେ ଅଛନ୍ତି? ନାଇଁ ନାଇଁ ଟୋଟାଲ ଏମାନଙ୍କର ଟୋଟାଲ ଅଛି 304 ନା, କିଏ ମିଶିବ। ଆରେ ସେଇଟା ହିଁ ରେଜିଷ୍ଟ୍ରେସନ ଟା ବନ୍ଦ କରିଦେଇଛନ୍ତି ଆଉ। ରେଜିଷ୍ଟ୍ରେସନ ଖୋଲା ଥିଲେ ସିନା ଆଉ ଟିକେ ବଢିଥାନ୍ତେ। ହଁ କୋଉଥିରେ, ହ୍ୱାଟ୍ସଆପ ରେ ନା? ହଁ। ଆଚ୍ଛା ଆଚ୍ଛା ଆଚ୍ଛା। ହୁଁ 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 ହୁଁ। କଣ ଗୋଟେ ତମେ ଚାଲିବ ଚାଲିବ ଲିଙ୍କରେ ପଶିବାର ଅଛି ବୁଝିଲ। ମାନେ ତାଙ୍କର ଇଣ୍ଡିଭିଜୁଆଲ ଲିଙ୍କରେ ପଶିପାରିବ, ଯେତେଟା ବି ମେଲ ଆଇଡି ମାନେ ତମ ଗୋଟେ ମେଲ ଆଇଡିରୁ ଯେତେଟା ପଶିପାରିବ, କିଛି ଅସୁବିଧା ନାହିଁ। କିନ୍ତୁ ଅଲଗା ସ୍କ୍ରିନ ରହିବାର ଅଛି। ଦିଟା ଦିଟା ଅଲଗା ଅଲଗା ବ୍ରାଉଜର, ନଟ୍ ଟ୍ୟାବ। ଗୋଟେ ଟ୍ୟାବରେ ସେମ ଧରିଦବ। ହୁଁ। ଏଜ ଥିବ ବୁଝିଲ ଆଉ କ୍ରୋମ ଆଉ ଗୋଟେ ମୋବାଇଲରେ କରିଦଉନ। ମୋବାଇଲ ଟା ଫ୍ରି ରଖିବ। ହଁ ଠିକ କଥା। ୟୁ ୟୁ ହୁଁ ହୁଁ। ହୁଁ। ଆରେ କିଛି କିଛି ନ କଲେ ସେମିତି ହିଁ ହେବେ ବୁଝିଲ କି। ତମେ ଷ୍ଟାର୍ଟ କରିବାର ଅଛି। ଆଉ ଆଡମିନ କିଏ ଅଛି ମହିଶାନ ନା? ହଁ ସେଇ ମିଉଟ କରିବା କଥା। ହଉ ଚାଲୁ, ଘଣ୍ଟା ତରକାରୀ ହଉ, ଆମେ ତ ଅଛେ ଦେଖିବା ପାଇଁ। ହଁ ଦେଖିବ ନାଇଁ ଦେଖିବ ମୁଁ ଦେଖିନାହାନ୍ତି ବୋଧେ। ହୁଁ। ଚାଲୁ ସମସ୍ତେ ମିଉଟ ଅନମିଉଟ। यूट्यूब ठीक चलती तो ସେଇଟା ଦେଖ ଟିକେ କହିବି। ମୁଁ ଆଉ ଗୋଟେ ଜିନିଷ କରୁଛି ଦେଖ କଣ ହଉଛି। ଫୁଲ ସ୍କ୍ରିନ୍ କଲି ହେଲା, ଏବେ କଣ ଆସୁଛି ଦେଖ। तो होगी अरे साला, ओ भाई, हाँ, अरे रो रो ओबियस रे बोधे रेकॉर्ड चलଥିଲା ବା ମାନେ କୋଉଥିରେ ଶୁଭା ଯାଉଥିଲା ୟୁଟ୍ୟୁବରେ କିନ୍ତୁ ଟିମ୍ ଭିତରେ କିଛି ଶୁଭା ଯାଉନଥିଲା ଯେ ମାନେ ମିଟିଂ ଭିତରେ ଠିକ୍ ଆରେ କ'ଣ ହେଇଥିଲା ହଁ କ'ଣ ହେଲା ମୋର ବ୍ଲୁଟୁଥର ଯେଉଁ ମାଇକ୍ଟା ସେଇଟା ଅନ୍ କରିଦେଇଥିଲି ଆଉ ସେଇଟା ରେକର୍ଡ଼ିଂ ନେଉଛି ଓବିଏସ୍ରେ ହଉ ହଉ ଓକେ ଏବେ ହ୍ୟାଲୋ नीट सेटिंग तो
हेलो
हाँ हेलो
गुड मॉर्निंग सर
गुड मॉर्निंग गुड मॉर्निंग
गुड मॉर्निंग सर
गुड मॉर्निंग
ଆଉ କାଞ୍ଚନ ମ୍ୟାଡାମ କୁଆଡେ ଗଲେ
मैडम अच्छा ये मैडम ए लाइन रे अच्छा
कांचन गुड मॉर्निंग
Good morning, good morning, good morning, ma'am.
ओके बेस्ट ऑफ लक
थैंक यू Good morning, sir.
Good morning, Anil sir.
Good morning.
Principal sir, can we start?
Now I am inviting
अंतर्जामी सर भी जॉइन କରିଛନ୍ତି sir.
नमस्कार.
Yeah, good morning to all of you. Am I audible?
Yes, sir. Yes, sir.
Yes.
नमस्कार.
So we should start.
Yes, madam, please.
Yes. Good morning to all. Hope all are safe and doing well. Myself, Dr. Kanchan Kumari, Assistant Professor, Department of Mechanical Engineering, Parla Maharaja Engineering College, Barampur, Odisha. Honorable guest of the occasion, SPA, SPIU, Odisha, Professor Dr. Antarjami Mishra. Honorable Principal Sir, Dr. Ranjan Kumar Sai Sir. Respected Speaker, Dr. Pradeep K. Majhi, Associate Professor, IIT Roorkee, and Dr. A.K. Chaube, Senior Principal Scientist, IIMT Bhubaneswar. HOD of Mechanical Engineering Department and TQ Coordinator, Dr. Tilochan Raut Sir. One of my colleagues, another convener of this webinar, Professor Sandeep Kumar Bhoi, my dear colleague, faculty member from other colleges, and participants from different industries. On behalf of the organizing committee, on behalf of the organizing team of APNC 2020, I welcome all of you to this one-day webinar on advancement in polymer nanocomposites organized by Department of Mechanical Engineering. During COVID-19 pandemic, there are many challenges regarding the conduct of online classes, seminars, conference, workshop, but it is as well gives the opportunity to all to explore the online platform to get rid of it. I request Principal Sir to preside over the meeting. Sir.
Now I invite the convener to proceed.
Now I request Dr. Trilochan Rao sir, HOD of Department of Mechanical Engineering, will address the gathering.
Good morning, one and all. At the outset, I, Dr. Trilochan Rao, along with conveners Dr. Kanchan Kumari and Mr. Santu Bhoi, on behalf of Department of Mechanical Engineering, PAPC Brahma, welcome our esteemed speakers, Professor Pradeep Kumar Maji from IIT Roorkee and Dr. A.K. Chaube from CSIR IMMT Bhubaneswar. The guest of the occasion, respected ASPIU, Professor Sundaram Mishra sir, our beloved principal sir, Professor Ranjan Kumar Swami, and esteemed participants to this webinar, APNC 2020. I wish a safe stay at home for you all in this difficult time of COVID-19. As individual performance is to team performance, so is sync material to a composite. As you all know that a nanocomposite is a composite material in which one of the components has at least one dimension that is nanoscopic in size, that is around 10 to the power minus 9. Basically, we come across three different design of nanocomposites like nano-layered composite, nano-filamentary composite, and nanoparticulate composite. Due to their large aspect ratio, sub-micrometer size, and unique properties, nanosensors, nanoprobes, and also chemical and for example, ceramic nanocomposites to solve the problem artificial implant. This would extend patients' mobility and eliminate the high cost of surgery. For example, the zirconia toughened alumina composite implants have potential lifespans of more than 30 years. Metal oxide matrix metal oxide particle nanocomposite having high sensitivity at lower operating temperature for detection of reducing as well as oxidizing gases. They have been used for fabrication of chemical sensors and biosensors. Now coming to advancement in polymer nanocomposites, the ease of processability of organic polymers combined with the better mechanical, optical, electrical and electronic properties of varieties of nanoparticles has led to the fabrication of many devices. Nanocomposites can be used in a variety of sensing schemes to enhance the performance of sensing devices and open new horizons in their applications. Nanoparticles, nanowires, and nanotubes of various materials have already had an impact on the field of chemical sensors, ranging from gas sensors to glucose enzyme electrodes. These are also being used for detection of proteins, acid, toxic gases, etc. The property associated with nanowires and nanotubes which enable us to modify them with other elements such as polymers or silica matrix imparts high selectivity to these devices. Nanocomposite-based sensors are expected to have a major impact on clinical diagnosis, environmental monitoring, security surveillance, and ensuring the safety of our food. Some of the areas of its present applications are drug delivery system, anti-corrosion barrier coatings, UV protection gels, lubricants and scratch-free paint, new fire retardant materials, new scratch or abrasion resistant materials, superior strength fibers and films, automobile and aviation industry. All these facts have motivated us to conduct the webinars, thereby providing the platform for exchange of the ideas in the field of polymer nanocomposites. I thank you all for making this webinar a grand success. So with this, I end my talk. Thank you all.
Now I am requesting SPI Odisha to please address the gathering and inaugurate our
Thank you, madam. Am I
Yes,
audible
sir.
to all of you?
Yes, sir.
Yes, sir.
Yeah. Respected Principal of Parala Maharaja Engineering College, Professor Swami, the tech coordinator, Dr. Raut, and the organizers of this webinar, Madam Kanchan Kumari or Mr. Bhoi. At the outset, I am thankful to you for providing me a privilege to speak a few words and inaugurate the webinar. Thanks a lot. This is a topic. In fact, my friend Dr. Raut has already spoken so many things on advanced utilization of nano composites. I would like to just give you a brief history. Composite was nothing new to the civilization. In the ancient civilization, when we were staying, or the human being, they were staying in thatched houses, you might have seen that the bamboo or wood or anything, those were reinforced materials, soil, or mixed with rice husk or anything, they were used as walls. So composite material concept started from that primitive time, but it was not called as a composite material. Later on, we thought of going ahead with some materials which will give you better strength, better longevity, better reliability, so that there was a discovery of composite materials instead of isotropic materials. Basically, all composite materials are anisotropic materials, but depending on the situation, depending on the utility, the analysis is carried out. Initially, it was in a very big number, no dimensions, nothing, bamboo or wood or anything. Then later part, we provided some reinforcement and the matrix. As a result, you get a composite material with better strength. Non-homogeneity is a part of composite material because the composite material is a tailor-made item which can be made or manufactured according to the design requirements of the members. So this is, then it was during 1970s or 80s. Beyond 80s, gradually this particle size or the particular researchers can be used, that is to the 10 to the minus time that you are telling. Then the homogeneity of mixing of fiber with the matrix will be almost 100% or 90%. As a result, the mechanics of composite materials. I am not talking about macro mechanics. I am talking about micro mechanics. There you will find, because of the uniformity, which will be treated as good as an isotropic material, and the strength will increase very much. But when we require some point of time, fibrous composites or long and continuous fiber composites are essential for making the composite. But when you are interested for increasing the inbuilt properties of the advanced material, then automatically nano composite or nanometric size particle reinforcement got the advantage over us. As my friend Dr. Rao told, that starting from drug delivery system, intracorporeal material, extracorporeal material, structural designs, I am talking that this composite material has taken a place in the arts, starting from navigation, aviation, or transportation, road transport or anything, or whatever you see, guns and cars. Composite material is playing a role. It has started in the aviation sector when the dome of Apollo satellite take it lightweight and high strength and making a streamlined model, a conical structure was constructed using carbon fiber reinforced composite. So friends, now imagine you see, when we are talking about Rafale, when we are talking about AS400, when we are talking about maximum transportation through air or navigation, which can work in a saline environment with a high degree of saline concentration without corrosion, without erosion, and having a reliable mechanical properties, electrical properties, magnetic properties, thermal properties, and so on and so forth, blah, blah, blah. Then definitely I think a nano composite will have a place more than the other types of composites. If you talk about a transistor or a thermistor, in a radio circuit or electronic gas, automatically, or a condenser, or electronics application, then automatically we think of a nano composite, which can work very well. The only difficulty is that how to get a nanometric size, and the particle size should be as all the particles must be of single size, and the measurement there. Usually chemical decomposition is done at our laboratory level, and we'll go ahead manufacturing nano composites. Carbon nanotubes mechanical engineering and structural applications, starting from automobiles, power plants, transportation, and domestic appliances, whatnot. So friends, I hope the topic that has been chosen in this particular COVID-19 situation, COVID-19 pandemic, the nano composites, what they are talking about, the drug delivery system, or transportation of materials easily because of the lightweight and high strength, and because of the longevity, made with bed in a COVID hospital, or made with saline bottle, or maybe any other thing which is applicable to the human conditions under COVID-19 situation, is a perfect decision of going ahead. My honorable speakers are there, those who are doing research in this composite materials. They may speak on certain aspect with respect to one particular matrix, metal matrix or ceramic matrix or polymer matrix. Doesn't matter, but it will definitely help all the participants to gain knowledge and accelerate the research on composite materials, taking into nanometric size of reinforcements into consideration. Matrix may be anything. I feel this seminar will help all the participants to a greater extent to carry on their research on composite materials. The speakers are good, they are on this job, and definitely we will be very much happy to listen to them. And I wish the seminar will be a grand success, or the webinar will be a grand success. With this, I inaugurate this webinar. I am once again thankful to Dr. Trilochan Rao, Dr. Swai, Principal of Parala Maharaj Engineering College, because at the last moment yesterday evening only he requested me, sir, why it is your topic, why don't you speak a few words? I told that I should be released by 10:25, so that I will be also inaugurating another seminar in another engineering college through video conference on waste management during COVID-19 situation. Thank you very much. Thank you. Thanks the organizers, Mr. Bhoi and Madam Kanchan Kumari, or whatever, I do not know, remember the name. Yes. I express my heartfelt gratitude to Parala Maharaj Engineering College for the privilege that they have given to me. Thank you very much.
Thank you so much, sir, for the valuable words. Now I'm requesting Principal Sir to give to tell few words.
Good morning to all. Honorable Chief Guest of this inaugural function, Dr. Antarjay Mitra, the President SPA of IQSK, SPA Odisha. Respected speakers, of this occasion, Dr. Pradeep Kumar Majhi, Associate Professor, Department of Polymer and Process Engineering, IIT Roorkee, and Dr. A.K. Chobe, Senior Principal Scientist, IMMT, Bhubaneswar. This, and I also welcome all the participants, those who have given their consent and participating this webinar. This college, Parla Maharaja Engineering College, is established in the year 2009 as a government engineering college, and it is the constituent college of Vijayapatnam Technical University, that is the technical university of the state. This college started with 4 branches. Later on, it has been expanded, and now we are offering undergraduate program in 9 disciplines and postgraduate program in 5 specialization in 3 departments. This college, being in Barampur, a age-old city, is prospering in a very fast manner. All the faculties are young and dynamic. They are carrying a lot of research work. Students are also very good. They are representing in different events in the state and the national level. They are bringing glory for the college. Also, though we are very young, as considering the number of batches passed out, but our alumni, they are being well placed and they are helping to bring the name and fame of the college to a better height. So, in this occasion, I give my special thanks to Dr. Kanchan Kumari and Mr. Sandeep Bhoi, who decided to have a webinar on a more talk of the day topic, that is advancement in polymer nano composites. I also thanks this TICUP 3 and the head of the department, mechanical engineer, who is the in charge of TICUP 3, for supporting financially and morally to make this webinar. In my view, the composite materials has the new generation material which is replacing most of the conventional metals. In particularly, when we are talking about a green environment, when a green environment is required, that means we want to reduce the carbon dioxide emission to the environment. So particularly aviation and automobile sector, where a lot of carbon dioxide generally dumped in the atmosphere, and because of the heavy weight of the vehicle now becomes very light because we are using these composite materials. Further, in the field of the green energy, that is wind power, the wind turbine blades are mostly made up of composite materials, and it is absolutely maintenance free and have a very long life. But the most important part of the concern, that is this nano composites should be, or any composite material should be sustainable and it should be green. So once more and more research is required to use green composites which will be biodegradable and will be help for a better environment in future. At the end, I wish a grand success of this webinar, and the participants will take with them good memories and the good outputs, as our conveners are chosen speakers from 2 different areas, one from hardcore research, that is CSIR lab, and other from academic that is Professor Majhi. I once again thanks both of the speakers for giving their consent and be a part of this webinar. Thanks to all. Thank you.
Thank you, sir, for addressing the gathering. Now I'm requesting Sandeep Bhoi, sir, my one of my colleague, to introduce the speaker to the participant with the reading of his biodata. Thank you, sir.
Thank you, madam. And thank you, our chief guest, Antariyapi sir, and our respected HOD sir, and respected principal sir, for giving their valuable time for the webinar. And so for today's webinar, we have invited two speakers, Pradeep Majhi sir from IIT Roorkee and Anil Chobe sir from IIMT Bhubaneswar. So the first speaker will be our Pradeep Majhi sir. He will deliver a lecture on polymers and its nanocomposite for aviation and aerospace applications. Before proceeding to his lecture, I will introduce him with his biodata. It is very difficult for me to address all the address his biodata, because he has very long career throughout this composite. And coming to his area of interest, he has research interest on functional nanomaterial, cellulose or nanofiber, graphene, silver nanoparticle, gold nanoparticle, and zinc oxide, and all these nanoparticle. He has lots of experience. Rather than all these nanoparticle, he has also expertise himself on polymer nanocomposite, and also which is based on synthesized nanomaterial also. At the same time, he has also many research paper on smart polymers and polymer synthesis and modifications, and as well as high performance polymer nanocomposite and properties of specialty applications. So mostly he has specializations in this polymer nanocomposite fields, and rather than his research activities, he has also awarded with many awards. Like he has got a Young Researcher Award in 2018 from Polymer Processing Society USA, as well as he has also got the Research Fellowship Award from the Matsume International Foundation, Japan in 2019. And at the same time, you will see he has many sponsored research projects under his belt, and from the different funding agency, like DST and Central Pollution Control Board, Government of India, Ministry of Human Resource Development, Government of India, and ACRB, and also from MHRD. So he has lots of vast experience on this particular field, as well as he has different membership from Aeronautical Society of India, Society of Polymer Science, and all these things. And also he has many years of teaching experience on this particular nanocomposite, on specifically polymer field. So he will deliver a lecture on polymer and its nanocomposite for aviation and aerospace applications today. So I request Dr. Pradeep Majhi sir to start the sessions.
Thank you, Mr. Sandeep. It's a nice introduction, and I'm very happy that there are a lot of people to listen to me. First of all, I would like to thank you, it's HOD Professor Raut, and today's guest of honor, Professor, and I'm really thankful that I'll be speaking in front of you related to a little bit of different subject that is little bit uncommon. So I'm sharing just 1 minute. Is it visible?
Yes, sir.
Is it visible?
Yes, sir.
Okay. So I'll be speaking today related to polymer, its nanocomposite for aviation and aerospace industry. Actually,
Sorry
I
to
have
interrupt,
been.
sir. The presentation is not visible, sir.
Madam, it is visible to us. Maybe you have network problem.
Visible to us.
It is clearly visible.
Is it okay?
Yes, sir. Yes.
Okay. Yes, sir. Yes, sir.
A very good morning to you all. I am Dr. Pradip Kemaji from Department of Polymer and Process Engineering. Today I will be sharing some of the experience while I was working at Indian Air Force as a polymer scientist. I was involved overhauling of Mi-17, Mi-8, Mi-17 V5 aircraft and AN-32 aero engine. During my stay, I have experienced different shortcoming of material and product, basically made from polymer and rubber material. Today I will be discussing some of the aspect of polymer and its aerospace application. Before going to the main topic, I'd like to ask a general question to the audience. Can you imagine any engineering without material? Because this question I have asked in one of the conference, and somebody has stand up and he told, yes, we can do it. And he was telling, whatever they are developing any software, the material part is absent. Then I have explained politely to him, if you go through the software, then definitely what system is required. The system means that's what you used to call it computer. In computer, hardware, whatever we are using, it's definitely some material is there. Without material, definitely we cannot think about any engineering. So, my answer of this question, whatever I have raised, without material, we cannot do any engineering. Material part is very important for any engineering. That too, whatever means the Department of Mechanical Engineering, I think they can appreciate better than anybody. They used to play the properties of this material to the engineering application. So, if I go to the material part with different specification, then there are mainly three standard of material. Number one is space standard material, mil standard material. Mil means that is the military standard material, and COT, that is the commercially of the trade material. That's whatever we are using day in, day out. In corrugated material, there are three different application area. Either it's maybe the industrial grade application, automobile grade application, and general purpose application. So today I want to specify my talk related to space standard or mil standard material. Whenever we are talking about space standard and mil standard material, the tolerance limit is very, very narrow. Why it is very, very narrow? Temperature means a range from -80 to plus somewhere 300, 200 degrees centigrade. And for military standard material, it's required always a very top material. It can withstand at any point of time with different environmental condition, as well as with any different shock absorbing capacity supposed to be there. We are researching in different aspects of material. Presently, most of the people, those who are working in the material part for the different mechanical application, they used to work on to do the researching on industrial grade material or automobile grade material, so that it can be utilized or upgrade to the mil standard material. So definitely some aspect is there to elevate the material to the mil standard material, because here, whenever we are talking about the processing part, then specific processing supposed to be required. Number one. Number two, temperature limit is important. Number three, its tolerance limit is supposed to be very, very narrow. And as a result of it, whenever we are elevating any material or any product to the military or space standard, then always that standard supposed to maintain and its life. And another important thing is here, its reliability always more than 200%. Now, as I am talking about the aerospace material, aerospace material, mostly whatever we used to see, it is metallic material. Whenever we are choosing any aerospace material, first of all, we used to check what is the cost of the material and what cost we can bear to upgrade the existing aircraft structure. Its design option of the airframe, structure component and the engine, fuel consumption of the aircraft, It must be lightweight so that its payload supposed to increase very much. Operational purpose of the aircraft, that speed, range, and payload. Power and fuel efficiency of the engine. In-service maintenance, one of the important parameter nowadays. Otherwise, if there is anything wrong in the sky, we cannot control. That's why in-service maintenance in air as well as the ground is very important. Safety, reliability, and operational life of the airframe and or air engine is very important. But what our chief guest was telling today, that is very important. After using this composite material or that particular material, whatever you were using in the aircraft structure, that end of life is very much important. That's why nowadays European Space Agency, American Space Agency, and as well as Indian Air Force and ISRO also, they are utilizing their recycled material for different applications. That's why it is one of the important aspects in the present scenario, the end of life of this particular product or particular component, that so that we can utilize this material to the next different application. If you see the what is the relation between the material science and material technology, material science generally it used to talk about its composition, atomic bonding, crystal structure, defect structure, microstructure, macrostructure. Then if you going to its application part, then definitely that is the engineering. Now, whenever we are trying to do the engineering, then definitely that property is very much important. Then most of the times we used to tell it's tailor-made property is required. Tailor-made property is required. Then what do you want to do the tailoring? We want to do the tailoring of specific properties. Then I am telling it's in general way. For a material, general properties is that density, stiffness, strength, fatigue, toughness, corrosion, and high temperature resistance supposed to be there. If you look at that, this microstructure to the atomic level, and this atomic level structure, it's combined to make a big structure, and you will be getting the total product property. That's why from microstructure to macrostructure is very important to know. If we know the microstructure, then only we can predict what material property we will be getting. So common material that is used in the used in the aerospace application, mostly you must be aware that aluminum and aluminum alloy is used in the aircraft structure, because its advantage is that it's moderate in cost, ease of fabrication including casting, forging, heat treatment, and definitely main advantage is that it's lightweight, high specific stiffness and specific strength, ductility, fracture toughness, and fatigue resistance, and also good control of properties by mechanical and thermal treatment. Means processing of this material is very easy. But if you see other way around, definitely some disadvantages there. It's low mechanical properties, elevated temperature. Mostly it used to get softened more than above 150 degrees centigrade for prolonged of time. Susceptibility of the trace corrosion cracking, corrosion when contact with the carbon fiber composite, because nowadays in body structure, aircraft structure, we are using carbon fiber based composite, and that is if we are using with that of the touching of aluminum alloy, it's make it corroded. Age hardenable alloy cannot be easily welded. That's why that is another issue. And another important material, titanium alloy. Today, whatever I am telling, I am not telling any specific. I am telling just overview of this material application. Whenever you will be going any specific parts or component of an aircraft or aeroplane structure, then definitely specific requirement is there. Based on the specific requirement, we used to choose the material. And titanium alloy is mostly used another material that has been used for a long duration of time because of its specific strength properties than that of the other material. And it's high strength, good fatigue resistance, creep resistance at high temperature, and excellent oxidative resistance up to 600 degrees centigrade temperature. Then again, disadvantage is that cost is definitely high as it's titanium alloy. But another difficult thing is that it cannot be machining it very easily as it's very hard. That's why from aircraft component, basically in the engine part, we used to use the titanium alloy. So now if I go to the next direction of the material, now today's morning, whatever we are discussing, that is a fiber polymer composite, and we are talking about the fiber polymer composite to reduce the weight of this aircraft structure, to reduce it's another advantage is that structural efficiency, fatigue resistance, corrosion resistance is there, radar absorption properties is there. It's one important, another most important thing is that low coefficient of thermal expansion. Whenever you are talking about the metal with increase of temperature, decrease of temperature, its thermal coefficients of expansion is different, but for the polymer or fiber composite, that thermal coefficient is very, very negligible. But if you see some disadvantages there, more expensive than the aluminum or aluminum alloy, manufacturing process is slow, anisotropic properties, low through thickness mechanical properties, low impact damage resistance, and flammability. Flammability because as you are using the polymer, then polymer maximum temperature resistance is 400 degrees centigrade temperature. Just I am talking about the high-end temperature for the specific fluorocarbon based or Teflon based material. But most of the material it used to get starting melting within 150 or 100 degrees centigrade like that way. That's why selection of the material, whatever I have told you, it's based on the specific requirement. Number one, whenever we are talking about the selection of the material in the aircraft structure, we used to look after the cost of the material, its availability, its manufacturing, ease of manufacturing, its density. It's supposed to be very low density material, that's supposed to be low specific gravity material, static and mechanical properties, fatigue durability, damage tolerance supposed to be very good, environmental durability. Any aircraft, whatever we are flying, it's supposed to fly at least 1500 hours or 8 years of time, then it will come to the base to do the repairing or overhauling. Thermal properties, thermally stable at low to high temperature. Cryogenic properties supposed to be very important because in the whenever it will be going to the high atmosphere, high altitude, the temperature is very, very less. In that particular temperature, thermal shock it used to get. In this particular temperature, if it is some crack is generating, then that crack will propagate and it's a disaster may happen. Electrical and magnetic properties, that is also important based on the requirement of the particular part. Now, I am going to the particular aspect of the polymer product in the aerospace. I think you can recall there was a space shuttle disaster that has happened on 1986, 28 January. That is a Challenger space shuttle disaster. Within 80 seconds of its launching, the space shuttle has get crashed. Can you imagine what was the reason of this crash of the space shuttle? There were if you see the Challenger model, then there were the one sealing ring in between the first stage motor, second stage motor, and third stage motor. In between first stage to second stage motor, first stage that is the gas propellant, second stage that is the liquid propellant, and third stage that is the solid propellant. And the second stage motor, that is the liquid propellant, whatever it was there, to withstand its pressure, we used to use one big sealing ring. This sealing ring is made of fluorosilicon polymer. This fluorosilicon polymer, its glass tension temperature, the glass tension temperature of the fluorosilicon rubber, whatever they have used, it is minus 12 degrees centigrade. And in USA, try to realize, just 1986, 28 of January, temperature was minus 20. And as the temperature was minus 20, that time, whatever its property was there, it's supposed to behave as a rubbery property. It was not behaving as a rubbery property. Rather, it was behaving as a plastic property. That's why it was not able to withstand the leak, and it was catch fire before it's supposed to catch fire. As a result of it, what happened? Due to this O-ring failure, total 7 crew members all are died. A membrane, gasket, rubber hose, paints and glue, then vibration isolator, siloxane, insulation of electrical wire, insulating rope, and another important thing is that you can appreciate without tire, you cannot fly. For the fixed wing aircraft, tire is important and it's essential component. And this tire is made of the rubber or polymer. That's why if we are not getting the actual property of this particular component or product, then definitely we cannot fly with precaution and with safety. So some product that whatever we have developed during my stay in 3 base repair depot in Indian Air Force in Chandigarh, that I'll be giving a little bit of just glimpse of this product, whatever we have developed. That this is the first product I have developed during my stay in Air Force. That this sealing ring is very small. It's very small, and it was AOG. AOG means aircraft on ground. Due to the unavailability of this sealing ring, the aircraft was on ground almost more than 2 years. To realize the sealing ring cost was maybe somewhere in 100 rupees, 200 rupees maximum. But due to the unavailability of the sealing ring and whatever we have developed, it was not passing with that of the working pressure of 140 kg, 145 kg per centimeter square. Then we have start digging what was the problem, step we used to follow: feasibility study, preparation of drawing, then preparation and approval of the test schedule. Then we have developed the compound, exact compound, then iteration process we have done. At least 6 to 7 different compounds we have developed and checked in lab, as well as in the final functional test. Then we have checked whether this material is working or not. Then finally we have done the functional test, endurance test. Then we have developed this material, and this product has been used in the final aircraft nowadays. Second, this is the diagram whatever we have developed. Second, this is the feedback, and for the mechanical part, that's tolerance limit. Try to realize 0.0245, making it's very difficult. It's making it really difficult. That's why whatever I was telling, the tolerance limit of a material in the aviation is very much important. This is another important product what we have developed, that is called the oil accumulator diaphragm. This oil accumulator diaphragm has been AOG for the long duration of time. What they used to do, whenever one aircraft is coming, they used to take it and they used to put in the new aircraft so that it can fly. Then you have started the reverse engineering, the material substitution. Then you have checked stringent test schedule to check whether aviation great aviation related test we have introduced. Functional and endurance test we have checked. Finally, in the engine test house we have checked, and finally we have developed this material, developed this particular product with that of the carboxylated nitrile rubber instead of only nitrile rubber, and it is in the use. And you cannot imagine, almost more than 2 crores of foreign exchequer we have saved by this development of this particular product. This is the design of whatever we have developed. And indigenous of the expandable polyurethane block for the external fuel tank. Then this is the polyurethane block, and this is polyurethane foam that has been used in the aircraft fuel tank. And you cannot imagine, without this foam, the aircraft cannot fly. Reason is that in the fuel tank, if we are not putting this foam, that with that of the vibration, with that of the vibration, then what happens? That fuel, that when it will collide with that of the surface of the fuel wall, then as a result of it, some ionization will happen. Due to the ionization, when it will reach to its fire point, then it may catch fire, and as a result of it, what happen? Catastrophic failure may happen. That's why, to reduce that type of ionization process, we used to use the polyurethane block inside the fuel tank, so that that type of ionization will not happen. We have introduced that MIL B83054B standard for the selection of the material, and that has been tested in the firing trial also. If somebody is AK-47 or something else, they are trying to break it, it may not break. Rather what happened, firing incident will not happen. That there was a great achievement we have done it. And another important thing, whatever we have developed, that self-sealing layer on the external fuel tank. In the external fuel tank, there are self-sealing layer inside before the outside of the fuel tank. And fuel tank is made of your aluminum alloy. In the above aluminum alloy, we used to use the natural rubber one means unvulcanized natural rubber coating, thick, somewhere in more than 15 millimeter of thickness we used to put it, and when we are putting it, then it will be self-sealing. Means if you AK-47, this is the trial has been done in the TBL, Terminal Ballistic Research Laboratory and DRDO lab, and we have seen there was no leak, or there was no fuel leak that is coming after the firing onto this fuel tank. This fuel tank has been developed in different procedure, that's inner liner, then fuel barrier, self-filling layer, reinforcement 1, reinforcement 2, then that we have used, and this has been under process for the for doing the patent that whatever we have developed. And I think I'm a little delayed. That's why it is better to go to the polymer nano composite. Nanotechnology in the aerospace industry, if you see in NASA's nanotechnology goal, there are 4 different groups. People are using engineering material structure, energy generation and storage, propulsion system, sensor and actuator, or different type of electronic device, and always there is a nano material that's been used for make it more efficient, to make it lower its weight, and as a result of it, what happened, structural stability is supposed to be there. Mainly what people are using, that most important, one important thing, people are using clay-based polymer nanocomposite. Today, I'll be telling little bit of polymer-based, clay-based polymer nanocomposite, and it's definitely it has some advantage than that of the normal material. Then we will be talking. I will be talking about the not nanotube. I will be talking about the carbon-based material, that is the graphene polymer nanocomposite, and I will not talk anything related to molecular engineering material, but I'll be talking about the cross-linked aerosol for the super thermal insulation. Whatever we are targeting the replacing of existing material, always we are targeted is that without deteriorating its property requirement, we are developing a material that is low in cost, number 1. Number 2, it's supposed to be very, very lightweight. In any spacecraft or any aircraft, if we are able to reduce its weight, then that is really good achievement for the aircraft industry or the aerospace industry. So first, whatever we have developed, that project has been given by the ISRO, Trivandrum, and this project was to develop a polyurethane coating. This polyurethane coating, normal polyurethane without using any nano clay, they used to use in their cryogenic fuel tank. In cryogenic fuel tank, there are different type of layers. In one layer, to reduce the permeability of the helium gas, they used to use the polyurethane coating. In the polyurethane coating, they used to use almost 8 millimeter of thickness of the material. But whatever we have developed by use of nanotechnology, we have reduced the weight, we reduced the thickness of this material to 2 millimeter. Try to realize it's a big fuel tank. And this fuel tank, cryogenic fuel tank, we are reducing almost 2 millimeters or 6 millimeter thickness we have reduced, and as a result of it, there is a reduction in the weight, and that has been used recently. Now, whatever we have taken as a challenge and what was the improvement, whatever we have taken, that just I have tried to discuss with you. Number 1, the material, whatever they were using during the time that was poor mechanical property, thermal stability was a little bit less, poor performance in the low temperature, and one of the important parameter, that is the high gas permeability, and poor dynamic mechanical analysis. Challenge was to improve the property with low specific gravity, with low viscosity, and another important parameter that you always supposed to keep in mind, that is low outgassing property. In this concept, I can tell you one story, because hydrogen embrittlement is always there is a problem in the aircraft structure. What is hydrogen embrittlement? I think in mechanical engineering aspect, you can learn a little bit of the hydrogen embrittlement. During the electroplating of cadmium coating, nickel coating, or zinc coating, we used to use the electroplating coating system. There is ionic mobility of cadmium or nickel. It is very, very high than the H+. So automatically cadmium used to get deposited in the the structure of the material. But you cannot deny, though ionic mobility of cadmium is higher than that of the H+, but still some ppm level hydrogen can deposit it there, and above that, that cadmium, if it is coated, then entrapped hydrogen will be there. When it will be going to the high altitude area, then what happened? That hydrogen, whatever it was inside, it is in the 1 atmosphere. But when it will go to the high altitude, the pressure difference, outside pressure is very, very low, inside pressure is very, very high. Then due to the pressure difference, hydrogen will try to come out from the system. When it will try to come out from the system, then it will make a path. When it will make a path, then hair-like crack it will generate. This hair-like crack, it will propagate to the structure of the aircraft structure. As a result of it, what happened? If you Google it, you will be seeing there are so many incidents related to hydrogen embrittlement. That hydrogen embrittlement, it's one type of degassing. And degassing means if there is an interrupt, means a low volatile organic component or any air or entrapped air is there, then always it will try to come out from the system. That's why whatever we will be developing a material, that's supposed to very, very low degassing property, means that will not generate any gas in the higher altitude area. That was really challenge. Other challenge was a little bit easy, but that challenge was very, very tough. But that test has been done in the ISRO premises, and they have certified, yes, low gassing property, what was the requirement, and it is passing. Then for what we have checked the challenge, then main challenge was to change the backbone of the polyurethane network, whatever ISRO till date they were using. Then we have developed a high cross-linking density type of molecule and alter the total preparation route, and finally we have used the nano filler to develop this polyurethane nano composite to reduce the permeability. First, this is the conventional process they used to use, that polypropylene glycol plus TDI in NCO-terminated polyurethane prepolymer they used to use, and finally they used to cross-link by the glycerol and TMP, and this is the polyurethane moiety. This polyurethane moiety they used to use in the coating system. This is the existing thing. What we have developed, we have used the NCO-terminated prepolymer, and we have used here hyperbunched polyol to do the cross-linking of the prepolymer, PU polymer. As a result of it, cross-linking density, it will increase manifold, number one. Number two, its permeability will reduce as cross-linking density is increasing. And we have used second generation, third generation, fourth generation polymer hyperbranched polyol. There are n number of OH group. As there is OH group is higher, then it will react all the NCO group. Definitely, we have taken its stoichiometry ratio. Three-dimensional cross-link structure has been generated. We have not stopped here. Then we have used different type of clay, and successful clay was clay set 30B. We have incorporated in the polyurethane hyperbunched cross-link polyurethane material, and this is the X-ray diffraction study that what was the maximum clay we can introduce there. That was the 8 pHr of clay we have introduced, and up to the 8 pHr of clay there was no peak, means up to that level all the clay layer, whatever it was there, it was delaminated. Clay layer is nothing but the tetrahedral octahedral tetrahedral structure. One tetrahedral octahedral structure, another tetrahedral octahedral tetrahedral structure. In between gallery gap is there. That whatever we are talking about, that gallery gap, that was totally diminished. As a result of it, exfoliated material structure we are getting, and as a result of mechanical property, other property, what we are expecting supposed to be very, very high. We are not stopped here. We have checked what is the microstructure by the transmission electron microscopy. This is the clay layer. This is the clay layer. We are seeing it here, and this clay layer is very much important for us. That will reduce the permeability as well. It will increase the mechanical property of this material. And totally exfoliated or sometimes exfoliated intercalated structure which have achieved. This is the atomic force microscopy. In atomic force microscopy, also giving the similar type of observation, whatever we have seen in the transmission electron microscope. And we have compared with the TEM versus atomic force microscope. Everywhere it is giving the almost similar type of observation. Now, we have checked what is the thermal property and in thermal property analysis. And if you see, almost 9-degree temperature is increasing thermal stability in the terms of maximum degradation temperature. Initial degradation temperature is somewhere increasing 5 degrees centigrade, though it is not too much high, but yes, it is increasing. It is increasing. But another important thing is the dynamic mechanical property. In the dynamic mechanical property, most important thing is that TG, glass transition temperature, whatever we are getting, it is -22 and we are getting -17. There is not too much effect of the glass transition temperature on the addition of the nano clay. And dynamic mechanical property at different temperature, yes, it is increasing. At -25 degrees centigrade temperature, 25% increment is there, 0 degrees centigrade, 50% increment is there, and 25 degrees centigrade, 75% increment is there by addition of 8 pHr of clay. 8 pHr of clay. Now, with DSC, we have checked with the different glass transition temperature, though whatever I have shown you, glass transition temperature in dynamic mechanical analysis, as its process is different, and we used to always report with the TG by DSC, differential scanning calorimetry, and here if you see, almost for -48, we are getting -41, though 7-degree increment is there, but still it is -40 range, means whatever we want to use in the low temperature region, it can be used. So, tensile property, that is what is important for us here. By 88% of clay loading, we are getting some increment of 139% of the mechanical property in terms of tensile strength. And here, that was the main criteria of the research, that whether we can able to reduce the permeability of the material or not. Yes, if you see the permeability of the material, it is drastically reduced. Almost half of the permeability has been reduced, we have gained. And reason is that the clay, when it will delaminate, that path, gas molecule, when it try to go to this from one end to the another end, if there is no nano clay, then what happens? It will go straight. Then its length of this tortoise path is very, very less. Then when it will get hindered by the nano clay layer, then automatically its path will increase, and as a result, permeability will decrease manifold. And just I want to compare with that of the clay, 30% of the 88% of clay clay. It is the summary of 139% increment by addition of 88% of clay, and elongation break also increasing. Modulus is also increasing, and modulus at 200% elongation, that is also increasing. This is the gas permeability what we have achieved. This is the TMP, trimethyl propane, that what ISRO was using. This is the microstructure by atomic force microscope. And if you see, whenever we are using the 4th generation high-performance polyol as a cross-linker, we are getting the reduction, huge reduction of the permeability. That was our motto, and we have achieved very precisely. And if we compare the property, of the existing material to that whatever we have developed without addition of clay, then with addition of clay I have shown you, but without addition of clay itself we have achieved. You see, by addition of, by using of high-performance polyol itself, we are getting 211% of mechanical property increment. Elongation is break also 48%. Now, if you compare, then you can realize earlier it was 1.83, then it come up with that of the 5.7 without addition of clay. Now it has reached up to 13.6. That is a huge improvement in the mechanical property, elongation of break, modulus at 100%, modulus at 200% also. Means this research, whatever we have done, that is really one future application in the ISRO. And I have visited in the ISRO premises in Trivandrum, and we have finally transfer the technology to the ISRO, and they are using definitely certain modifications they have done with their requirement, and definitely recently they are using our developed material in their system. Now, as a scientist, I want to tell you what is going on there, why that type of situation is happening, how delamination of the material or clay that is happening. This is the clay structure. This is the clay structure. This tetrahedral in between, middle is the octahedral. Then above there is the tetrahedral. This is another tetrahedral in between octahedral. Then again tetrahedral. In between there exchangeable cation is there. Now this is the clay layer. We can so like that way. We want to incorporate our material inside it. This is called the intercalated material, and this is called the exfoliated material. And we want to do the exfoliated of the material so that all the clay layer that will delaminate, and as a result, polymer filler interaction will increase manifold. So, current concept of intercalation was that whatever polymer we are using, polymer will try to penetrate inside the clay layer, and as a result, the delamination will be happening. But we have seen in this concept, the efficient delamination cannot be done. Then we have proposed and we have checked with the delta Gibbs free energy calculation by work of addition with the polymer to the clay. Then we have proposed this is not the principle what people used to explain, and we have published in this concept in a one book chapter. Here, what happened? First, whatever polymer it is there, it will try to absorb the outside material, outside clay. It will get absorbed. Then it will try to make a little bit of excess gallery gap. Then when it will increase the little bit of gallery gap, rather we can tell it's intercalated, then other polymer chain, it will get some space to interact and go to the inside. Now, if I show you some with cartoonistic demonstration, then you can really realize very easily, this is the existing model that people used to tell that polymer chain will go to the inside, and big chain again it will go, and as a result of it, we will be getting intercalated or exfoliated structure. Now, proposed structure is that, proposed mechanism is that this is the gallery of the clay. Now, polymer chain, the big fat man, the polymer chain, it will try to go inside, but it is failed. Then what happened? Then this big fat man, it will try to get absorbed. By absorbing of this and shearing of this material, then what happened? Then it will increase some gallery gap inside it. When it will increase the gallery gap inside it, then what happened? Then other polymer chain can enter, and small, big, and a very big molecule can go inside, and as a result of it, what happened? We will be getting exfoliated of clay. And our achievement is that if we are able to get that exfoliated of the clay, then all the property, whatever we are expecting, then we will be getting enhanced. Another important here you have to recall, you have to remember that whenever you will be using any clay, nano clay in the polymer matrix, then polymer filler interaction is one of the major role that used to play in the polymer nano composite. In polymer nano composite, what we used to check whether polarity difference is supposed to be very, very minimum. As a thumb rule, polar will dissolve polar, non-polar will dissolve non-polar. In this concept, whenever we are using the polymer clay, then sometimes we used to do the modification of this clay so that interaction to the non-polar polymer, it will be very good. As my system is polyurethane, it is polar in nature, we can straightforward, we can use, but still we have done a little bit of modification so that interaction with that hydrocarbon chain, it will be very good, and as a result of it, we are getting the better result than that of the existing what people have reported earlier. So this is the polymer clay nanocomposite that whatever we have developed, and we are working the self-sealing polymer for the space coating material. Then you can appreciate if in any biological system, if there is any injury, then what happens? It will get cured over a period of time. It will get cured over a period of time, and if we are able to mimic the same thing in the structure during its any damage or anything else, that is something beautiful. Then if you see, this is the chemical repair, what I want to show. Chemical repair, what we want to show. And we want to mimic the biological system here also to develop that type of strategy. Then what we have developed a capsule-based composite, capsule-based coating. And definitely what we intend to use whatever I have explained to you, hydrogen embrittlement. In the hydrogen embrittlement, when it will generate the crack, that immediately it will get repaired. The encapsulation based curing system we have introduced in the polyurethane coating, and as a result of it, what happened when this is the one material, this is the catalyst, another is the raw base material, when it will get some crack, then both the material will close to each other, and as a result of it, total material will be get cured, and you will not be seeing or you will not be finding any crack or any scratch mark on it. That's why this is externally you can do it also. And matrix is made up your some catalyst we have incorporated with the capsule, and matrix, when catalyst will attach with the matrix, then it can do the same working like that way. This is the morphology of whatever we have developed, and if you see, this is the 200 micrometer level spherical structure we have got it, and this structure is very important because mechanical stability is supposed to be there during the brushing, but when it will generate the crack or any scratch mark, then it will supposed to break. Otherwise, it will not work. Then we have checked its surface roughness as well as its property. This research is going on, and definitely we are thinking we will be getting a very good a good property of the microsphere, so that it can be utilized in the different aspect of application, not only our aircraft structure, but for any automobile structure, we can introduce this type of material as a coating. Another material we used to use as a self-healing ionomer. Self-healing ionomer means that is the some sodium or some zinc or copper plus ion. It has some tendency to close to each other. When some ports will be coming, then it will degenerate. It will go to the different shape. And when it will withdraw stress, then it will come close to each other, and self-healing self-healing system can occur like that way. So this that's why just I can tell you that self-healing material are the way of unbreakable engineering for the future, and we are working in it, and hopefully we can do little bit of better material for this particular purpose. Graphene-based polymer material for the aerospace application we have developed. Whatever we have developed earlier, the clay-based nanocomposite. In the clay-based nanocomposite, whatever we have faced some problem, though I have not told you earlier, the problem is that clay, that it as it has a OH group, always it is hydroscopic in nature. As it is hydroscopic, sometimes interspecial energy between the polymer to filler, it is always reduced over a period of time. That's why life of the clay-based polymer nanocomposite, it is not too much high. That's why we have introduced, why not to similar type of layered structure. The layered structure means that is a graphene. We can use the graphene in the aerospace application also. Here, this is the development we have done. 1-part synthesis of graphene oxide by sonication assisted mechanochemical approach we have developed. Most of the times, what happened that Hammer's method and modified Hammer's method, what people have used to report, its requirement of time requirement to make a graphene oxide material more than 3 days to 4 days. And we have developed this process so that ultrasonication and delamination, as well as the oxidation of the graphite material, which happening simultaneously, and we are getting this product within a 12 hours of time. That is a great achievement, that we have reduced the time to getting the graphene oxide material with minimum time with good good yield. This is the schematic presentation that we have used, that whenever we are using that sonication bath in the reaction itself, then graphene means that is the basically one layer graphite is the graphene. And here, what we used to do, we used to do the oxidation first. That when we are doing the oxidation by KMNO4, then what happened, OH or carboxylic group that will attach. When it will attach, then automatically gallery gap will increase. In this gallery gap increment, we used to use that sonication And due to the sonication, bubble formation will generate. This bubble formation will help to do the delamination. Now, actually, this is the graphene oxide, whatever we have achieved. But this graphene oxide, again, if we want to use as a graphene analog, then we have to do the reduction of this graphene, so that reduced graphene oxide is the analogous of the graphene. It's graphene that used to develop by the vapor deposition process. Here, this is the APSM analysis that whatever we have developed, and this is the almost flake-like structure we are getting, and it is agglomerated structure. Finally, if you go little bit of the high sonication speed and long duration sonication, single layer graphene, we can get it. But till date, single layer graphene is very difficult. So this is the TM microstructure. If you see that whatever we are getting, that thickness of almost we are getting 1.4 or 1.6 nanometer. But till date, if you see the reported value for the graphene or graphene material is somewhere 0.73. Means we can conclude from here, this is not the only single graphene layer. We are getting some 2-3 graphene oxide layer attached to each other. As a result of what happened, we are getting little bit of higher thickness. Notwithstanding that thickness value, our purpose to use this material to enhance the property of the polymer material. Then we have checked whether we can do this improvement of the thermoplastic polyurethane material or not. Here, in situ polymerization process we have done by PTMEG, by plus MDI, this NCO material, isocyanide material. Then we have got it NCO terminated pre-polymer. Inside, we have used the graphene material. This graphene material has, definitely it is graphene material, means reduced, this is graphene oxide. In graphene oxide, as there is a OH group and carboxylic acid group, this will react with the NCO terminated pre-polymer, and urethane linkage it will generate. Means the interaction, physical interaction, instead of the physical interaction from most of the other composites, here we are making a chemical interaction to enhance the product property. If you see the product property in terms of mechanical properties, then you will be surprising that by addition of 0.01 pHr, try to realize 0.18% of the addition of the nanofiller, we are getting strength increment of 280%. And when we are adding 0.01 weight% of reduced graphene oxide, we are getting 245% increment. Similar way, elongation of break also increasing 420%, and here 170%. Try to realize one thing. Any material, if it is giving the increment of the mechanical property in terms of strength, and as well as it is increasing the elongation of break, means material will going to be very, very tough. But area under the curve will increase very much. As a result of it, this is called the synergistic effect of the nanofiller, that is giving the increment of the polymer matrix in both the way in terms of mechanical property or in terms of elongation of break also. And we have checked the toughness. That's why you have checked the toughness. Toughness is increased by 400%, and we are getting the increment of toughness 200%. Now, if I compare the graphene oxide and reduced graphene oxide, then you have to appreciate in reduced graphene oxide, there's a lot of OH group and carboxylic group. That's why physical link was there. Physical link means that is the chemical linkage was there with that of the polyurethane, with that of the polyurethane graphene oxide. But when we are reducing the graphene oxide, then what happened that due to the reduction, the carbon containing, oxygen containing group was reducing, and as a result, number of OH group or number of carboxylic groups get reduced very much, and as a result, interaction point was very, very less. That's why increment in the mechanical property and toughness, it was get reduced. That's why whatever we are getting the 400% of toughness increment, here we are getting the only 200% of mechanical property improvement. So I am going to the in different directions. Whatever I have told you, that three-dimensional porous structure I will be talking for the cryogenic fuel tank that has been used in the aerospace structure, aerospace fuel tank material. Then here, I think you can recall, any liquid nitrogen tank used to use, it used to be very, very heavy. Why it is very, very heavy? One outside metallic component is there, inside inside one silica-based aerogel, which is thermally highly insulating material we used to use. Whenever we are using the silica-based material, then what happens? Silica is always specific of it is very, very high. That's why our target was to reduce the weight of the cryogenic tank. If we are able to reduce the weight of the cryogenic tank, then that will be very, very a great achievement for us also. Now, what we have started, before going to that thing, just I will tell you what is aerogel. Whenever we are talking about the gel, that is the basically polymer material. Whatever we are talking about, the aerogel means air plus gel, that is called the aerogel. In any big structure of the material, hydrogel, you must be heard about this material. Water plus polymer, if it is called, that is the hydrogel. In this particular position system, if we able to evaporate the all air, water, then and without disturbing the structure of the gel material, polymer material, then air will be introduced inside. That is called the aerogel. This aerogel, and do not confuse the aerogel with foam. Foam and aerogel, it is almost similar thing, but when we will be talking about the aerogel, but its void density and its pore size is 2 to 50 nanometer. But when we will be talking about the foam, its pore size always higher than that the nanometer level, and porosity is very, very high, more than 90%. But foam porosity is below 80% or below that also. That is called foam. And if we are able to develop that type of aerogel, the aerogel, as it is almost 90% of only the air, then what happened? Air thermal insulating property is very, very high. Air thermal conductivity is 25 milliwatt per meter Kelvin. Now, this property we want to, that thermal insulating property we want to utilize in our system. Here, what we have done, then we have chosen nanocellulose as a material. In the nanocellulose material, first we have done the hydrogel preparation by gelation process, then direct freezing. In this particular position, what we have done, we have minus 20 degrees centigrade, we have freeze it. Means water that is in the ice form, and as well as the gel, that whatever we have used, the nanocellulose, it will be intact. Now, direct sublimation, if we do, that is called the either supercritical drying process, otherwise we used to use in our laboratory, that is called the lyophilization process. In the lyophilization process, then water, whatever it was inside, it will get evaporated and total gel remains same. And here, though I am showing it's 90%, in our laboratory, we have received almost 90 6%. It's a huge porosity. To realize this is the lightweight, it can sit in a marigold flower, and it is very strong enough to withstand the almost some 1 kg of weight, and it's flexible so that you can make it mold, or that you can put it in different orientation like that way. That's why what I want to make tell you here, then definitely we have do the research here. What will be the density and what will the porosity based on the result and different concentration of the cellulose nanofiber in the water media. Then we have seen almost 0.18% and 1.28% concentration of CNF, that is cellulose nanofiber, is more than enough to get that type of porosity as well as very much low density. Notwithstanding that, we have done the X-ray microtomography, that is called the CT scan microscope. In the CT scan microscope, we have checked whether there is any defect or not, and you will be surprising, there is no defect inside the material whatever we have developed. And if you see that whatever you have used here, 12 kg per meter cube aerogel we have used, whatever density we are getting 8 to 20, and here 12 kg per meter cube aerogel we have shown the result here. This is the other material we have shown. Then if you see, and the most important result here, with 1% of the concentration of cellulose fiber inside it, we are getting 25.5 milliwatt per meter Kelvin. 25% 0.5, it's air of what I told you, 25 milliwatt per meter Kelvin. Here we have achieved 25.5 milliwatt per meter Kelvin. But recently we are getting another interesting phenomena, and we think we will do, already we have apply for the patent. We are getting almost 18 milliwatt per meter Kelvin by addition of the cellulose fiber also. In cellulose fiber, what we used to do, we used to do some hydrophobic modification. With that of the hydrophobic modification, we have seen one very good observation of whatever you are getting, that thermal property is getting reduced manifold. Manifold. This is the mechanical property of what we have to show it here. The mechanical, it is very, very strong. Whatever I have shown you, if you see, 1.78% of the material, that is mechanical property is almost 120 like that way. And we are getting mechanically strong material, elastic zone, plastic zone we have calculated, and we have published this paper in Materials and Design. And so what I want to conclude from here, whatever the material we have developed, definitely we are working on it to more further development, and we are not stopping here, that we are starting to do the fabrication of the structure of the cryogenic tank. Then already we have a collaboration with Variable Energy Cyclotron Center in Kolkata, one BRC, Bhabha Atomic Research Center lab. They have one facility to go minus 270 degrees centigrade by use of liquid helium. And already we have doing the testing there with the low temperature behavior of the material, though we are getting some problem, but I think we will be getting some good result from this research. Now, but whatever we are discussing for aircraft structure material, in aircraft structure material, carbon fiber has been used very huge way. What is carbon fiber? Carbon fiber basically it is high strength material. High strength material. And if we use this high strength material to a composite, this composite can replace very well with the iron and lightweight aluminum also. And it's another advantage is that it's exceptionally mechanically strong and weight is very, very less. That's why it is used extensively in rocket, missile, aircraft structure, sporting goods, car, etc. We used to use this material. The characteristics of the carbon fiber is that it's excellent thermal resistance and chemical stability, excellent electrical and thermal conductivity, excellent flexibility and strength and dimensional stability. And carbon fiber is used in the reinforcement of the material of the composite. And for LCA application, it's light compact aircraft structure, almost airframe structure, if you see all airframe structure is almost all are basically carbon fiber. All this is the carbon fiber composite. If you see, total structure is made of carbon fiber that is made in basically in Air Force. DRDO has developed this LCA aircraft structure, and that is in the flying condition nowadays. So, what is the demand of carbon fiber? Carbon fiber demand is very huge in the industrial application in terms of windmill, car, sporting goods, and definitely whatever I have told you in the aerospace application. If you see, there are so different type of carbon fiber. That's one what is a pan-based carbon fiber, pitch-based carbon fiber, and other fiber like glass fiber. What morning professor was telling, glass fiber we are using, aramid fiber we are using, boron fiber we used to use. But if you see, pan-based fiber has a tremendous application. Reason is that it is cost-wise little bit less than that of the other material, and it cannot. Glass fiber or aramid fiber cannot match the property with that of the pan fiber. Now, polyacrylonitrile based carbon fiber, that is the pan, whatever I have told you, polyacrylonitrile carbon based fiber. Here, this is the structure of the carbon fiber. Whatever we are getting means the process. If I show you the process, then you can understand. Oh, if I tell you the process, what we used to do first, acrylonitrile polymer, we used to do the acrylonitrile material, basically this is monomer, we used to do the polymerization process. After the polymerization, white color polyacrylonitrile material we used to get as a polymer, it is powdery material. This powdery material, addition of some solvent, specific solvent and spinning technology, then it used to get the fiber formation. Then when you will be getting that is a polyacronyl fiber, it is not carbon fiber. Then after that fiber, after getting that fiber, then there is a process that is called the carbonization. If you do the carbonization of this polyacronyl fiber, then it will convert to the carbon fiber. In the polyacronyl carbon fiber, then what we used to do here, carbonization, in the carbonization, in the absence of oxygen, we used to burn. If it is a bond in the in absence of oxygen in the specific lower temperature, then what happens? All hydrogen, all oxygen containing compound that will go out from the system, only carbon skeleton of the polyacronyl material, it will be there. As it is the totally 100%, almost 100% carbon material, that its mechanical property is very, very high. This mechanical property we used to do in the used in the system so that it will help us to do the property improvement of the structural application. Now, just if I coming to the little bit of end, then whenever we are talking about the aerospace material or aerospace product, then there are different approval process of this material as well as the final product. In the certification process, that is very, very important because we never compromise the quality of the final product as well as the raw material that has been used in the aerospace application. First of all, we used to check whether that supplier is approved by the quality audit personnel. If it is the military, then RCMA, they used to give the certificate that is called the Regional Center for Military Airworthiness. And if it is a civil, then that is called the Directorate General of Aeronautical Quality Assurance. They used to give the certification to the raw material as well as the final approved material also. But supplier as well as the material that's supposed to be approved by the specific audit quality person, audit committee person. The development, whatever we are trying to make a product, each and every stage, Six Sigma as well as one standard is there, that is the aerospace standard is there. We used to follow in every aspect to check whether in every aspect we are taking care of the product quality or not. In every aspect, that RCMA person, basically RCMA is a representative of CEMILAC, that is called the Center for Military Airworthiness Certificate. But for the normal aircraft, the DGAQA, they used to give the certificate. This certification agency, they are very much stringent. They used to follow all the protocol that has been written in the their protocol. And getting pass certificate of a particular product, it's required sometimes very long time because reliability of this material is very important in the final application. Because try to realize that most of the times I used to talk whenever we are talking about the aerospace industry or space material, space industry, then we are working with a 0% tolerance, a 0%, 0% tolerance and 100% efficient material we supposed to use. Then error limit supposed to be 0%. If there is anything wrong in the air, that nobody can save. Nobody can save you. Basically, that is the reason that we used to give the importance to our pilot because they are taking risks to fly our aircraft. Okay, and the prediction of the advanced composite structure in US Air Force, if you see, we are age of 1980s, then after the 1985 and 1990, if you see, advanced fighter aircraft, whatever we are using, this is the advanced composites come to the market and reduction of the titanium and steel alloy that is going down, and over a period of time, if we are seeing, we will be using most of the, in the internal part, in the external part, we will be using the advanced composite material. And you will be surprising one, it's a good information regarding this carbon fiber composite aircraft made in a Boeing 787, whatever that is Dornier, you people used to talk, that Dornier, that maiden aircraft that has flight 15 December 2009, the total structure has been made with the carbon fiber. And that's why almost 30% reduction of the weight has been done. And as a result of it, they can increase their payload in the aircraft for the carrying the goods or human beings itself. A polymer nano composite market to take up. Basically, we are in the age of 2020. That's value almost 37 billion of US dollar. we are expecting. And if you see the revolutionary fact forces, that 1971 to 1985, textile was the one of the important material. That railroad was the another invention. Automobile, I think it is come to the saturation. Computer, we are the age of computer. Still, if you see, we are come to the saturation. We are come to the near saturation. But in the nanotechnology, I think this is the means we are here. Still, there is a lot of scope to do the development with that of the nanotechnology to ease up our life. If you see nowadays, earlier computer structure, it was very, very huge. Now we come to that system that it's with a pinpoint you can get all information. That is the development of the nanotechnology in the information technology or computer technology itself. And I think that will be the future technology that we are talking about. I'd like to acknowledge the financial support from the IIT Roorkee, Science and Engineering Board, Government of India, Department of Science and Technology, Government of India, ISRO, and definitely this is my research team. I have to always appreciate. Without the student, I cannot do anything, and this is my strength of my strength for me. Thank you very much. Any question? I think I've done it a little bit 5 minutes ahead. So any question you please, I'm ready to answer it.
Thank you very much, sir. It is really a informative session for all the participants and
thank you very much.
All of us. I think it is really helpful for all the participants to get a brief knowledge about this polymer clay nano composite as well as this molecular material and cross-linked aerogel. And as a mechanical background, I think most of us are from mechanical metallurgy, material science background. I hope everybody will be a little bit of comfortable with this hydrogel embrittlement as well as this dynamic mechanical thermal analysis, what we have already expertise and all these things, as well as the story that we have shared with the relations with the ISRO and your time spent with the ISRO Kerala. Then it is also quite interesting, and as well as one of the most interesting topic what I found out is that your self-healing polymer that is really one of the interesting topic. And at the end also that hydrogel, and I have not actually personally I have come across this hydrogel that is used for mostly medical backgrounds like
Mr. Sundar,
surgery.
Mr. Sundar, it is not the hydrogel. Actually, I was talking about the aerogel. Hydrogel, we are not using in the system. We are using the aerogel, but preparation of aerogel that will be come through the hydrogel only.
Yes. That aerogel part which is useful as a composite also. It is quite briefly described here. And the carbon fiber, most importantly, where these aerospace industries are using, and that also quite elaborately discussed here. I think most of the participants are well acquainted with all these things. So I request all the participants, those who want to ask any questions or any queries related to all this. So you may unmute yourself and ask question to Professor Pradeep Mari, sir.
Sir, this is Dinesh Babu. I have a question regarding mixing of polymer with biocompatible nanopowders.
Whenever we are talking about any mixing of a polymer to any nanofiller, whether it is a biofiller, whether it is a synthetic filler, most important thing you have to keep in mind is polarity difference. If there is a polarity difference is very, very high, then automatically it will not be miscible or compatible. The terminology is compatibility. Whenever we are talking about delta G of mixing, that's supposed to be 0. If it is delta G is mixing of negative, then it will be very, very miscible. And we want to make a miscible material. Here, that miscibility factor, it will come up with that of the its polarity difference. Whenever we'll come close to each other, that's why what I told you, polar will dissolve polar. Then if my material is polar and filler whatever we are using polar, then its miscibility will be very, very high. But again, notwithstanding that, the polarity whenever we are talking about, then again they are supposed to be very different in the polarity also. Like polyurethane, whatever I was talking, its polarity, and its clay, its polarity. Polarity of the clay is very, very high, but polarity of the polyurethane, it is polar, but it is not too polar that of the with clay. That's why we used to do little bit of modification of the clay so that polarity difference supposed to match or come to almost zero. Then compatibility or miscibility will be very, very good. That strategy we used to use. And during the strategy, then in the industrial scale, then we have so many parameters during mixing. Because initially, when we will start the twin screw extruder, then there we used to keep in mind, first you have to rotor speed supposed to be very slow, then you have to remix again, then it will do the pace to interact with the polymer to filler, then only you will be getting. Okay.
Okay, sir. Okay, thank you, sir.
Okay, sir, you're most welcome.
Hello.
Yes,
Pradeep, sir.
Okay.
Yes. So there is some questions in the chat box of YouTube also. What is the role of atomic packing factor in any atomic structure, sir?
Atomic packing atomic packing is very important for the mechanical property of a material, because sometimes what happen, like if you compare with the crystal structure of the material, means whether it is BCC structure, whether it's FCC structure, whether it's a simple cubic structure, that we used to calculate the packing factor on it. When there is a packing factor will increase, then mechanical property in terms of hardness it will increase. And if there is an increment of hardness, then other mechanical property, if we are able to make a long metallurgical bond, then automatically mechanical property will increase. But here, whenever you must be aware and you must be knowing that when you will be using the high packing material, sometimes it cannot be mixed with other material, because it will not allow to interact. It will not allow to interact, or it will not allow to go to its inside. That's why sometimes there is a requirement of defect, and that's why, and in metallurgy you must be knowing, then we used to see intentionally that we have to see whether some defect is there or not. If there is a defect, from that defect we can work on it. I think clear, though I am not specialist in metallurgy related to packing factor, I think this is the way we used to see. But polymer nanocomposite, whenever we are seeing, and that we will not seeing the packing factor, rather we used to see the surface area. When it will increase the surface area, then filler polymer interaction it will be high. And in polymer, there is basically for rubber, there is thin entanglement, there void formation will be there. That our nanomaterial or any filler that will go and sit in the particular void part. And as a result of it, packing of this particular composite, it will get enhanced, and as a result of it, mechanical property will increase. Okay, I think I have cleared your doubt.
Yes, sir.
Start కొట్టు.
Oh, sure.
Start కొట్టి ఫీడ్బ్యాక్ ఫారం ఇచ్చాడు చూడు లింక్.
Hello, sir. I'm not getting it.
Any questions can be asked to sir? Hello, madam. Any other questions that is asked in the YouTube?
No, there is no question in chat box, sir. In YouTube, there is no questions. Any other questions from here in Google Meet? Please let me know.
Sir, one more question, sir, from Dinesh Babu.
Yes, please go ahead.
Yeah, thank you, Mr. Sandeep, for your mechanical engineering and the conference, this webinar organizer. In that condition, actually, the single metal cannot perform all the requirement as per the design of the equipments or any components. In that case, we have to choose a different combination of the materials where you have to, it can be a metal, it can be a ceramic, it can be a polymer, depends on the functionality and the requirement of the atmosphere where this component is going to use. We have to design the material. So, and in this, our previous speaker, Dr. Pradeep K. Majhi, IIT Roorkee, he has explained the audience many things about the polymeric matrix composite and how the polymer matrix composite is a lot of useful in aerospace industries, how the dimension tolerances, property tolerances are very much required in case of the defense application, where the life saving and the this fighting of the spirit of the army, which is main requirement, where this actually the material tolerance and is the main features, where we cannot tolerate even a nano scale fly in the material, which can lead to a catastrophic failure of the material, and that's why it will be a loss of life and loss of the economy of the country. So we have to very much careful about this when we are going to design a material for a critical applications. So with this, I am coming to my topic. So let me just open the slide. Hello. Is this slide is visible to you, all of you?
Not yet, sir.
Yes, sir, it is visible now, but it is not in full screen mode.
Yeah, just yeah, this is in now in full mode.
Yes, sir.
So I think so, and it is visible to all, and I am audible to all. So just for your confirmation, I am going to start the presentation right now. Is it visible to all of you?
Yes, sir, visible.
Yes. Okay. Thank you. So actually, the today's my topic is the lightweight metal matrix nano composite for aerospace and automobile applications. So before going to just to this particular topic, I am just going to just a small introduction about our institute, what we are doing, and what are the facility here, which maybe from in this current situation not possible, but from your institute, many people may have visited IMMT, and in future your students or any faculty can also visit and utilize the facility. So just a brief introduction about this institute. So actually the institute is one of the CSIR, Council of Scientific and Industrial Research Laboratory, which is in the near Acharya Vihar in Bhubaneswar, and it is the actually CSIR. All you must be knowing that it is the most highly funded government organization, where we are doing in the vast area of the research, from medicines to material to aerospace and so many things. And under this CSIR, there is 39 institutes which are spread in different part of the country. In the Odisha, this is the one institute where we are doing mostly the research on the minerals and materials. In this one, we are doing basically supporting the industry related to mineral and material development, and we are improving their process, we are solving their problems, and we are also providing their solution. And and cost-effective technology so that their performance and their product can be actually comparable to the world level in comparison to the world market, so that they can compete with the world market. So in the institute, I am working in the advanced material technology development, advanced material technology department, having around 20 scientists and around 5 technical staff, and around 40 to 50 students are there. So we are working in the mostly the development of the alloys and then composites, and then through a liquid metallurgy as well as the powder metallurgy route, we are working on the coating on the thin film and thick film coatings. We are also working in the ceramic area, so gemstone processing and other ceramic materials for coating as well as the ceramic components. So here are the few facilities at the in this department. I'm not totally showing the institute facility, but we are having in the Department of Advanced Material Technology, where we are working for the materials development. So this is the atmospheric spray plasma facility, which is actually the spray plasma gun. It is in the robotic attachment, robotic system, so that any component of the 2D or 3D we can coat the through a atmospheric spray plasma system. And then hydrogen plasma smelting reactor, where we are using the hydrogen gas to generate this plasma, and this is basically was developed for this green steel production. Actually, this was funded by Ministry of Steel project. It was a 10 crore project, and we have worked on this to produce the steel without any coke and usage of the coal. Then this is the submerged arc furnace, where we are using this furnace for this making the different metals production by this arcing process. This is the in-flight thermal plasma processing. So it is used for this thermal extraction of the materials. And this is vacuum induction furnace, micro hydrogen plasma reactors, then CVD systems used for coating, sputtering. Then this one is the hot press. So here this hot press actually having vacuum arrangement. We are using it this for this powder compaction and sintering, where this by this powder metallurgy we are producing a sintered component made from for the alloy as well as the composites, and then in-flight plasma reactors. So these plasma reactors are used for this this titanium production and as well as other metal production. This is actually this is the microwave sintering setup, and this is the composite making this stir casting setup. So used for the composite production. And then some other facilities like a pulse laser deposition unit, DC arc plasma reactor, then moving bed plasma reactors. All these plasma reactors are used for this extraction of the metal. It can be a titanium, it can be a iron, and different base products. We are using these reactors to actually get a value-added metals from the base products, and also some metals from secondary. And this is the actually dual die flattery ball mill, where we are doing the mixing of the material, so that mixing of the material can be used for this alloy making as well as composite making, flattery ball mill, cold compaction units. Apart from the actually the processing facility, we have an advanced characterization department, and in our department we have a lot of characterization facility which is used for this basically for this advanced material characterization, and that actually decide the material property and way of the manufacturing, so that we are actually in the right track or wrong. So that's why we can correct ourselves production process or the manufacturing process, so that we can get a facility. Also universal testing machine, nano electrical systems, micro hardness measurements, carbon sulfur analyzers, and we have a glow discharge spectroscopy, which can be used for the different chemical elemental analysis in the material in the solid form, and then microscopy, where we can stop this. Yes, actually, I'm going to start presentation now. This is the outline of the presentation, and just tell about some background of the composite material, and then I will give a short introduction of the composite material, their classifications, applications, synthesis processing methods. Then I will come to directly to the lightweight composite material, where we have produced some composite materials for different automobile and aerospace application. So some case study I will discuss, and then summarize data. Mr. Sandeep, I'm audible? Yeah.
Yes, sir. Yes, sir. You are clearly audible, sir.
Okay. Okay. So coming to the materials. In materials, there are the many types of material. Generally, there are the 4 types of material which we are using, and from different variety of material, we are producing a new variety of material. That is the another way of classification of the material. But mostly we have a 3 type of material. You can say that metals, where we have aluminum, copper, steel, nickel, zinc, whatever in elemental form you are seeing, pure metals, that are the metals. And then polymers, polymers having different type of polymers, and single material cannot perform the duty or the design requirement of the components. So in that case, we have to go for a new kind of materials which can sustain in this harsh condition or in the environment where the material actually will be used. So in the suppose you can see this type of fiber polymer matrix composite. So, and when the fibers are discontinuous fibers, the fibers are not a continue, and some continuous fiber. Continuous fiber means from one end to other end, and discontinuous fibers where the fibers are like a discontinued. So and this for the composite fabrication, you need a high cost, because you need a reinforcement, and you need a different specialized process of making. You need a different matrix material, and to combine this matrix and reinforcement, you need a very high temperature, sometimes very different property, very different process requirement. So that makes this fabrication very costly, and a complex mechanical characterization. And in that case, because in this one the reinforcement and the matrix both are together there, but in certain conditions you have to find out the property of the matrix and the property of the reinforcement. So in that case, it is very difficult to characterize how much contribution of this reinforcement in mechanical property and how much contribution of the matrix. And in that, whether we have to reduce the reinforcement or whether we have to increase the binding between the reinforcement and the matrix. So if you have to get particular idea that how much the contribution of this strength in the, or how much contribution of the creep property in the reinforcement and also the matrix. So individual characterization is very complicated in that case. So and also complicated in the repair of the composite structures. So because if suppose somewhere there is a flaw or somewhere there is a defect in the composite, so if you want to repair, in the case of the alloy, it is very easy to repair. You fill the same composition of the material at that point and you can get a same property. But in the case of the composite, it is very difficult to repair the composite because your particular point, your properties should not be matched, and that's why the stress razor will be at that point, and ultimately the material may fail at that point. And high combination of the required property may not be available. So in that case also, when we need a high combination of properties, suppose we need a high temperature strength as well as we need a very light weight. In that case, sometimes it is not possible to make a composite where it can be stand around 4,000, 5,000 degree temperature, and also it has a very light weight. So that combination is not possible. So these are some limitations. So coming to the next, where these are just a simple classification of the composites. This is the polymer matrix composite. When we are using as a reinforcement matrix material as a polymers, and reinforcement could be a metal, it could be a ceramics, and it could be any other material, and it can be a combination of the 2 or 3 materials. But matrix is the polymer, so it is called polymer matrix. Metal is matrix, so metal matrix composite, ceramic matrix composite, and carbon-carbon composite. And another, already I have told that the classification different is when you are different type of reinforcement, then the composite, again, it will be a particulate reinforcement, or it can be a fiber reinforcement, or it can be a flake reinforcement, and it can be also a continuous fiber reinforcement, discontinuous fiber reinforcement. So, and it can be also a, if you are using fiber as well as a particulates together in a composite, then it can be a hybrid matrix composite. So these are the simple kind of, in the nature, there are the different composites are available. So that is a very good example of the nature itself making a composite as per their requirement, or they are designing itself. So suppose you see the bamboo tree is a one form of, this is a composite. If you just cut the bamboo stem, you see there are a lot of fibers in that bamboo. So and it is fiber is made many fibers, and they are together with the binded with this matrix type of material. So it performs the strength, which gives the strength of this bamboo. And also bone, if you see the bone cross section, in the bone cross section, you look, there is a porosity level is different from surface to inside, and these porosity level actually are making it as a composite material, because air property at the surface is different and inside property is different. So it is not a one kind of material, it is a mixture of material. You can say this is the actually a natural composites. Skin also made of several layers, it is also a composite material. This tortoise shell, this cover is a composite material. This tree, palm wood, the cross section you see, there is a different colors you are seeing in different. So this is actually different property from surface to inside, and this material having a different composition cross section wise. If you look, the property vary from surface to center, and the strength, all these are vary, and the material material, that's why it is called a composite material. So coming to the nano composite, which is our aim today. So in the nano composite is a kind of a composite where one of the either matrix, either reinforcement of the one of the constituent of the composite, you can say it should be a nano scale. Nano scale means your material of one of the either length, either thickness, whatever, it should be less than 100 nanometer. So in that case, it is called a nano composite. And nano composite gives a very different property that from a normal composite, because nano size range, the property of the material vary and behave differently. So there are these many examples of nano. This is a fluorines is a kind of a nano size balls, and the carbon nanotubes. It is in the form of tubes, but this is in the one dimension is in the nano forms. So it is called a carbon nanotubes. Graphene sheet. It is it is also a nano 2D nano reinforcement. It can be used for reinforcing the either metal, either ceramic, either polymer, any one of this. And 3D graphite. This is also in the 3D nanoforms. So graphite particles can be used as a very less than 100 nanometer size, can be used as a reinforcement. So basically nano composite, where one of the matrix are the reinforcements and one of the dimensions should be in nanoforms, and that gives a completely different property of the material. So here are the different type of the reinforcement. So, and it can be a very classified for the size, on their size and shape, and also their distribution in the matrix. So you can see that the quantum dots, nanocrystals, clusters, these size basically comes around 1 to 10 nanometers. They are used for insulators, semiconductor, metals, magnetic materials, etc. And other nanoparticles like a ceramic, oxide, carbides, nitrides, whatever, then these generally when we are reducing the size, it comes in the range of 1 to 100 nanometers. So these are also one type of reinforcement. Nanowires, in this lengthwise it is bigger, but this diameter will be less than 100 nanometers. So it is a kind of a fiber or reinforcement type. So it can be used for a metal matrix composite, semiconductor, oxide, sulfide, nitrides, and nanotubes. Suppose carbon nanotubes. This can be used for a fluorescence layer and different other purposes for electronics application. So, and these these materials are the nanoforms. So that's why it is property is quite different from the normal materials, and it has a different. I have now going to tell you it is in the nanoform. So that's why it reduces the melting point. Melting point. Suppose a material in the nano, a compact of the material in the micron size, and when the material in the compact is in the nanoform, so the melting point of the two materials are different because of the surface of the atom on the surface is quite different. In the nanoforms, the surface area will be high, and that's why melting point will be low. And in the case of the bulk material, your surface area is very low, so that's melting point is very high. And there is a lot of difference between same material having nano size and also having a micron or a millimeter size. And the material should be ultra hard. When it is in the nano size range, due to the many defects in the material, so which makes it a ultra lowest hard and ultra hard. So that depends on the how much defects in the material. Even in the alloy or any composite, if you see a very microstructurally, there are some defects in the material as well. But when you are reducing the size, the defect size also you are reducing. So that's why your hardness also vary from bulk material to nanomaterial. Then optical property also changing with the material. Electrical conductivity also changing with this size of the your particles or the crystalline up into that bulk material. Magnetic property, self purification, these are reactivity also changing. If you can see this is the color, how this is changing with this size of the particles in the suspension, this suspended liquid. So here is 150 nanometers, and here if you are decreasing the size, how the color are changing. In this, if you look the gold when it is in nano forms, it looks like this, and when it is in the bulk form, same gold, but it is in bulk form. Bulk form means actually this is not a, I'm not talking about the ring. I'm talking that in the ring there is the crystals are there, and the crystals again makes the grains, and grains again makes this bulk form. But the crystal, whatever here in this ring, that is in the micron size, either it mostly will be micron size, but here the crystals are in the nano size. So that's why the color of the material changing from nano to bulk because of their surface area. So coming to the application of the nano composite, so in the nano composite for the lightweight application, we are using a lightweight matrix. So that's why in the lightweight matrix, the material density will be low, and that's why a small same cross section or same weight of the material, if you take a steel and same weight of the material you take the aluminum, so in that case, so you will get a specific strength higher than in case of aluminum. So if you are making it aluminum by reinforcing with other material and making it as a composite, so by using a hard ceramic particles or a hard metallic particles, which can in the nano form, which can make the high strength of this. So that's why you are again increasing the specific strength of the material. So it has a large applications like a transport industry, cylinder, piston, car body, wheels, gearbox, housing, etc., which can be made from this lightweight, high strength applications. Then energy applications where you need a very light weight materials which can sustain also in different environment condition, and also have a sufficient strength to perform the duty as per the design the component. So these are the different energy applications, suppose the flywheel, solar panels, electrical wires, hydrogen storage, etc. Here, and it also because of lightweight, if you see that magnesium, it are mainly used for this computer laptop covers and processor, sensor, chips, electronic packaging material. So these are the composite material because of their lightweight and other property. They can use for a different packaging material, electronics usage, and so on and so forth. So, and some composites it have a very advanced use in the case of different applications, aerospace applications like fighter planes, steel. This is a carbon fiber where the actually the radar can also not detect this one, so that's why it is called a steel fiber. The material having property so that radar wave will not reflect the signals coming from radar. So that's why it has a very strategic applications, and this BMW, which is using actually either carbon fiber roofs and other components of this body, so making a energy efficient vehicle by reducing the weight of the vehicles. And many Daewoo, Ford, all these companies are nowadays using around 25 to 30% of the composite material, so to reduce the weight of the vehicles. And they have a plan in near future to increase their carbon, composite compositions and lightweight for the lightweighting around 60 to 70% of the components. And some critical components where the composite cannot be used, that definitely they have to use with this go for the alloys. But most of the weight reducing component, even engine body casting, all these are the nowadays are made by this composite material, lightweight composites. And some actually very strategic applications, the composites are also used in the case of this bulletproof vest, where these different kind of materials are used to avoid the penetration of the bullets. In here you can see that there are 3-4 layers of the composites. In that, this is the upper layer are the laminated composites. In middle layer is the armor substrate. In the inner layer, that is a foam, which is just near to the body of the soldiers. So here there are the different layers having different actually different layers having different properties, so that it can reduce the penetration of this armor bullets and etc. And in the laminated composite, this has a high damping capacity and high resistance to the wear, so that it can avoid the bullet to penetrate it. And then armor substrates, which are ceramic materials, which also reduce the speed of the actually the bullets. And then this is the foam, which is a very actually soft kind of material, where this is actually just adjacent to the body, so that it cannot actually it can reduce the stress what is coming from the bullet to the body, and so many other applications. So now coming to the metal matrix composite. In the metal matrix composite, as I have already told you that the metal matrix composite, the part of the matrix is the metal, and the reinforcement will be different kind of, either it will be a ceramic, or either it can be a metal, either it can be a polymer. So and these are the different actually the components which is made of ceramic. This is the liner, piston, and of this the 2-wheeler, 4-wheelers. And the property, how you determine the property of the actually composite material when you are adding the 2 or 3 part of the constituent in the composites. So then you have to know that individual property, what are the individual contribution of the different part of the composite. In the alloy or in the metal part, there is a single component, so whatever the property that is belongs to that component. But in the composite, there are 2 or 3 components. So what are the, when you are testing, you are getting the single property. So single property cannot be actually it decides the whole component property, but individually what are the individual component property. So it is actually decided by the and predicted by the mixture rule. So and here suppose you want to make determine the density and what composition you have to mix. Suppose if you are mixing the aluminum with 30% silicon carbide, so what will be the density of your component? So in that case, you have to find out the density of your aluminum and your silicon carbide. So and then what are the weight fractions of the volume fraction of the aluminum, and what are the volume fraction of the silicon carbide. So in that you can know that is suppose the density of the composite, then fraction of the matrix and density of the matrix, and then fraction of the actually filler material or the reinforcement, and the fraction of the density of the filler material. In this equation you can know that the individual part what are the actually different density of the different components, and same time strength, thermal conductivity and other property also you can get by this formula. The composites are used for different temperature applications, and that's why suppose if you want to use your within 200 to 400 or from room temperature to 400 degree temperature, then you can use the PMC, polymer matrix composite, where there are the two types, thermoset and thermoplastics. But if you are using your material is designed for a higher temperature, then you have to go for these different other materials. So these are the metal matrix, and this is the ceramic matrix. This is carbon-carbon composite having very high temperature stability. Before that, this is the fiber. This is the ceramic reinforcement composite. So it is next to the carbon-carbon fiber. And metals are here in this range, where in that metals superalloys are very much having very high temperature stability. So that these are different, actually kind of variety. If you are application oriented at the requirement of your application, you can choose which material we have to go for and for the particular applications. So now I'm going to the how the composites are actually metal matrix composite are made, are nano composites. So there are three different methods to make the nano composites. There is a solid state processing, where in the solid state processing there are the 2-3 methods are there. First one is diffusion bonding, where you are adding the layer by layer the materials, base material and other materials, and then you are applying the pressure from both sides. So the materials in between are in the layer why they are diffuse each other and they forming a bond. So that is one way of the making of the composite sandwich structures or material. And in other case, if you this is the powder consolidation process, where you have to take the material in the powder form. Suppose if you are making aluminum silicon carbide composite, then you have to aluminum in the powder form, silicon carbide in the powder form, and you are putting the material here in the die by mixing the aluminum and silicon carbide. So that's applying the pressure, and same times you are heating also. So that in both way the material get compressed and sintered. So you get a compact product with the mixture of 2 or 3 materials. So this is the called a powder consolidation process. The powder consolidation process also a different type, where you can use the uniaxial pressing. You apply the pressure from one direction and heat the powder from in the furnace, and same time apply the pressure, and you get a compact in the form of the your die design. It depends on what is your design of the die. So you can get the component directly in the form of a die, and it is uniaxially you are pressing. So here the property will be uniform in one direction, may be vary from other direction. So but for that you need to press from all direction. So in that case you have to press from all direction. This is called isostatic pressing. In isostatic pressing you are applying the pressure to the material from all direction. Your powder in the die, and die may be heated or maybe in the cold condition, and you can apply a pressure from all direction so that you will get a uniform compact. Then next is the semi-solid methods, where you are giving heat to the material so that it is in semi-solid region. So it is not a melted, not in a solid, complete solid form. It is called a semi-solid. Semi-solid means just it is a viscous form. So the material put in the you are in the form of your die, make a and heat in such way that material gets softened, and use the filler material in this one, and you can get this directly the component in the form of your die design. And then liquid state sintering or liquid state forming of the composite, where your one or both of the matrix are both may be in the form of the liquid form, and one will be in the form of liquid, other will be in the form of a solid. So in that way, your preform and your molten metal. So suppose preform in the solid form, your molten metal in the liquid form. So then adding reinforcement in the form of a solid part, and you are mixing by a stirrer, and then you can cast it directly, or you can allow the cast in the mold, and either you can cast through a bottom pouring method. So there are a different method also in stir casting method, and you can make a suppose aluminum silicon carbide composite. If you want to make, you can melt the aluminum, and you can put the silicon carbide after melting, and you apply the stir the material, and then you can cast in the mold. So this is called a stir casting setup for making a nano composite. Then pressure die infiltration process, where you are actually making the molten material, and your preform will be here, and then you apply a pressure from this side, and by the pressure it goes to the preform, can infiltrate the liquid part in the preform, and it become a composite material. So now I have given just an idea about the composites, how they are different applications, and how they are manufactured by different process. Now I am going to show you some case study where we have actually done some work to prepare a nano composite. So here I have prepared a magnesium aluminum nano composite. This was made for different automobile and aerospace components. Suppose this is the we have prepared for HAL Coraport, the gear housing box application, then engine blocks, and some other. This is for actually helicopter part, fighter helicopter. So these are actually use of this composite. So now I am going how actually we have prepared this composite by this powder metallurgy route. In the powder metallurgy route, we have taken this magnesium aluminum powder, we did it mechanical alloying, and then after mechanical alloying, you can see this is your mixture powder. After mechanical alloying, then the powder get hot press by uniaxial hot pressing, so you can get this tablet form in the bulk tablet form, and then further it is extruded, and you after extrusion we have got in the rod form. So and then we studied the property of this composite. So this is actually the parameters what actually used in this process. The temperature was 300 to 400, the pressure and the vacuum level, and then the extrusion, what are the conditions are used during the extrusion. So finally we have extruded 10 mm rod to a 4 mm rod, so that we can reduce the further density of the composite, and we can increase the property of the composite. So this is actually the uniaxial hot press, where this is the die, and you are putting the powder, mixed powder in the die, and the die is fitted with this this induction furnace, where it is the coil, induction coil is there in between the die fitted, and this is the upper punch and this is the lower punch. So the upper and lower punch apply the pressure for to make a compact, and this induction heating will provide the heat at the, so that in the we can get a required sintering temperature and required pressure and required time, so that we can get this dense product. So after getting the tablet, what I have shown in the earlier slide, the tablet again used for extrusion. So for the extrusion, actually you are seeing there is the copper type of rod, but the inside there our aluminum magnesium material, but copper was used in this form, and the material was fitted with this hollow part of this this capsule, and this capsule are again put in the die and apply the punch pressure, so that the copper actually used for to get a soften and provide a slipping to the die, so that the material inside will be extruded. It will not fracture or it will not get any defect. So after that we can remove the copper, and our exact material will get, and we can get the property of the material. So here this is actually the magnesium aluminum powder was milled with different hours, and the phases what we have got in the after milling, and we got this magnesium aluminum intermetallic phase, and some magnesium oxide also forms, but these phases evolve not after different milling hours. You can see that there is a gamma phase here very low, but as milling increases, the gamma phase increases. So gamma phase is the intermetallic phase, so we need this phase, which is the strengthening phase, and we have to reduce the oxide, but anyhow that oxide on the surface of the particles which is remain up to the, but the oxide peaks are lowering. So because of the some oxide are on the powder particle, which during milling it remain in the composite form. So and you can see that this is the particles during milling, different hours, 5 hours, the almost agglomeration taking place, the all particles become a bigger size, and then if you are increasing further milling time, the particles are getting fractured and the size reduction taking place, but the complete reduction even after 100 hours, you can see that the particles are not come to the as a required size range in the nano size range. That's why we again do is cryomilling. In cryomilling, actually we are milling in the cryo temperature range, so that this material become a brittle, and ductile to brittle transition take place, so that material become a very fracture with during the milling. So that's why we did a 3 hours cryomilling, and we got a nano size range of the particle. Here you can see that the size of the particles are not in nano, but the crystallite size, whatever in the, because in the milling what happens, you are milling, but your crystallite size become a nano, but the particles again some agglomeration take place. So then particle to particle agglomeration, so that particle size is different than crystallite size. So if your crystallite size in the nano range, means your material is in the nano range. So here I have shown you clearly that how the mixing of the two constituents, magnesium, aluminum, takes place during the different milling hours. If you see that this is the 5 hours of the milling, then what happened? This is the green one is aluminum and red one is magnesium. So aluminum, what happens? This surrounds covers the magnesium particles. And when again you are milling, there are the cracks forming the magnesium particles, and the aluminum going inside the cracks in the magnesium particles. And again, if you are going to 100 hours, you are seeing that the most of the particles, aluminum magnesium mixing take place. But in this region, mostly the magnesium even still is there. So that's why again it was filled to make a cryomilling, so that the material can be a uniform. So here you can see that the material magnesium, aluminum almost uniform, and the size is also in a nano crystalline range. So that's why this is a uniform mixture to make a composite. So that's why it was done for 3 hours cryomilling. Here actually the hardness during the milling was taken. This is the mixed layer. This is the magnesium. So here you can see that the hardness also changing during the milling time. Here you can see that the crystallite size, how the crystallite size going to reduce and it coming to the nano size range. So that's why we have find out the crystallite size by XRD measurement, and from XRD we have used the Ritwell fitting analysis, and from Ritwell analysis we have found the lattice parameter and also the crystallite size. So actually this is the pure actually this mostly the metallurgy part. I'm not going through in the detail of this. Here this is the transmission electron microscopy picture of the powders, and you can see here clearly the size of the nano crystallite. This is the one particle, but the one particle is made of many crystals. So you can see the small dots are the crystals, which was confirmed by the side area pattern of this TEM microscopy. So from this we have confirmed, say that this is our powder is now in the nano crystalline size range. Even your particle could is bigger, but your material in the nano size range. So, and that material was used in this aluminum matrix. So the aluminum and this was the mixture of the magnesium and aluminum what was produced by the mechanical milling or alloying. So these two was made for the composite, and the composite part you can see this is the reinforcement, this all are, and the different 10%, 20, 30, 40% volume fraction of the reinforcement was used. So 10% you can see very small particles, but here some agglomeration, here again some agglomeration of the reinforcement, here again agglomeration. But more or less the reinforcement are distributed evenly in the matrix. And by the XRD also you can see how the reinforcement and the matrix are changing the XRD pattern. And here we did EDAX line scan analysis and on the particles. So on the particle you can see this is the reinforcement, this is the matrix, and in the reinforcement how aluminum and magnesium are changing. So in the between after the sintering you can see the aluminum is low but magnesium is high, but here this is the diffuse region where aluminum magnesium are quite in the same range. But so that's why this is the three kind of composite. This is the magnesium, this is the aluminum magnesium region, and this is the magnesium. So this is but bonding is very perfect, and you can see by this image. So that's why here we have get the property. So suppose when without reinforcement you are getting strength around 120 megapascal, but if you are going to 10% reinforcement around 300 megapascal we are getting strength. But if you are going to 20% reinforcement we are getting around 600 megapascal strength. So the 600 megapascal, but same time we are actually reducing the ductility certain amount. Here we have a 60% ductility, but here up to 30%. But it depends on application. But when we have need a very high ductile material, so that in that case we can add only 10% reinforcement. In that case we will get a strength up to this 300 megapascal, but we will not lose ductility. But if we need a very high strength of material, then we will go for a 20% of the reinforcement, and we will lose ductility, and we will get around 30% of the strength of the material. And in this case, suppose if we take a grain size as a lambda between the particle spacing between two reinforcement, and we plot different volume fraction of the reinforcement lambda power half by the equation of this lambda power half and the sigma value, so we get a straight line. So it means that the composite material also follow the same rule as our alloy follows. So it means our composite is a homogeneous composite, and we are getting the property as per the alloy. So this is the actually a good point in case of the composite, if we are making a uniform composite, because if your composite is not a uniform, it is no use. You are getting a property, certain direction property is different, another direction property is different, and certain part of the composite you are getting different property, another part getting different property. So that's why you cannot design that any component from that composite. So your pre-requirement is your material should be uniform, your property should be uniform in all directions, and so that it can use for any component. So and again we have studied to the effect of the particle size of the reinforcement in the matrix, and we have taken different range of the particles. This is from 80 to 100 microns particle size in this composite, and then again we reduce the range 40 to 80, and then the 20 to 40 micron size in this one, and then minus 20 micron size of the reinforcement particle in this composite. So all four type of the composites we prepare, and using different size of the reinforcement range, and we have tested the two stress to strain curve, and you can see that how the property are varying. If you are having a bigger size range, your property low, also you get a serration. Serration means your material not behave uniformly, means material have some defects in the some defects or some inhomogeneity in the so that's why the reinforcement and matrix are not behaving homogeneously. But if you are reducing the range of particle size, the serration reduce, and also the same time we are getting a higher ductility and higher strength. So that's why the range of the particles also is very much important in the case of the metal matrix composite, and also the distribution of the reinforcement is also important in the case of composite to give a uniform property. So the fracture surface here also was analyzed in all the four size range of the particles. In why we are getting serration, the bigger size particles, if you look that this is the cracked in the case of bigger particles, so that giving a serration when the dislocation move, and it's obstructed by the bigger particles, the particles fracture, and you get a higher stress and then lower again. So that's why it giving a serration in the stress strain curve. But in the case of the lower size particle, you can see the particles are like a ductile behavior, behaving like ductile matrix, and particles are like a rod type of they are not fracturing with so it is deforming uniformly. So next case study, we have prepared this aluminum calcium intermetallic composite, which is the aluminum matrix and aluminum calcium intermetallics were added in the aluminum matrix. So the aluminum calcium matrix, this intermetallic was prepared by mechanical alloying, and this reinforcement again added this aluminum matrix. So by the same process as you have earlier seen that we have prepared the composite, and this composite was actually engine block casting, oil pans of this automobile are basically can be used this. So this is the XRD, how the phases forms, and where we have to stop the milling, and what will be the size of the crystal, which is I have already explained in the earlier. So it is like a same here how the actually the phase and how the stability of the phase are there. We have taken XRD at different temperatures by synchrotron radiation, and you can see that how the phases are changing from and different energy. So which temperature should be a better for sintering temperature so that the phases remain. So by this way we can get by the high temperature XRD, we can get that whether this entering temperature will be sufficient to stabilize this phase, or we have to reduce this entering temperature. That we can get from this one. This is again the phase transformation study. This is again the composite, where this you can see the aluminum calcium particles are there, but it is in cluster form when you are increasing. But here we have studied in two different methods. First two are simply blended. The aluminum matrix and reinforcement are blended in this one. But in this two one, the mechanically milled the reinforcement. So we have to study that whether this mechanical milling has an effect or not. So that was studied in this one. So here you can see the mechanical property of the blended one aluminum, and this is mechanically milled. So there is a huge difference in the property of the mechanically milled. Mechanically milled will give a uniform distribution, as well as the particle interface between the matrix also improves. That's why we are getting a better property in the case of the mechanically milled composite reinforcement distribution compared to the manual blending process. This is the pure aluminum. This is the 20. B20 means 20% of the reinforcement by blending, and this 40% of the reinforcement by blending, manual blending. But this is the mechanically blending, 20% and 40%. So in that both cases you are getting better property. Here you can see that the mechanical blending is better than manual blending. So now I'm going to show that the third study, which is the tungsten copper functionally graded nanocomposite. It is different from normal composite. Here we have prepared the functionally graded composite, means the composition from one end to other end varied by different powder metallurgy process. So that's why it is called a functionally graded material. So actually it is prepared for this nuclear plasma facing components, where the temperature is very high, around 10,000 degree temperature for these nuclear facing components, where no material can stand at that 10,000 degree temperature. So in that case, so single material cannot perform the duty of this plasma as a plasma facing component. So that's why a need for generated for a composite material. So any other material, because here the nuclear active atmosphere, where this many species of the nuclear actives are there. So in that case, the only tungsten can stand in that atmosphere. Other material cannot, because it will be eroded, and it will be neutron will bombard the material and material will destroy it. So that's why we use the tungsten, but tungsten having a low thermal conductivity, so tungsten cannot stand up to 10,000 degree temperature. It should be actually the heat should be extracted from tungsten to the so that it can stand at that temperature. So for the heat extraction, the tungsten should have a high thermal conductivity, but tungsten should not. Tungsten has not a high thermal conductivity. That's why here we use a tungsten copper layers, so that this copper can take a heat and it can transfer from coolant side. So I'm going to tell you here that suppose the heat flux is here, it is plasma facing, this tungsten side is plasma facing, and copper is here, and the cooling water is flowing this side. So the heat should come from this side to this side, so that the tungsten should always maintain a cooling condition, and the temperature should not go above that melting point of the tungsten. So that's why, but tungsten copper having a immiscible system, and both having a high difference in thermal coefficient of expansion. So that's why it is very difficult to weld to tungsten and copper to each other. So that's why we have actually chosen to make a tungsten copper functionally grading, so that we will not directly build tungsten and copper, but slowly we will reduce tungsten by copper, and the other end will be completely copper. I am showing you here. This is actually the process work here. This is the 100% tungsten, and the slowly we have reduced the by copper, so that the heat from tungsten side to copper side, it so flow easily, and because of the thermal conductivity difference, if suppose we will build tungsten and copper, it will be again will be cracked from interfacing surfaces, because the thermal conductivity, the thermal expansion coefficient of both material having different. That's why here slowly grading was created, and this is the material, and this was made in the spark plasma sintering setup. Spark plasma sintering was used because in spark plasma sintering, because here is a tungsten and the copper. So if suppose we will heat the material, it will be melt the copper, but it not melt the tungsten. So that's why tungsten copper building sintering also will not take place. But in this spark plasma sintering, what happened? It depends on the resistance of the material. Heating and the heating temperature also depends on the resistance of the material. So where it will give more resistance, more heating will take place, and where it takes less resistance, less heating will take place. So in that case, the total compact having different temperature. It depends on the composition and temperature also, so that we would able to make the sintering by this process. I'm showing here the component made by three process: the cold pressing followed by sintering, and this is the hot pressing, and this is spark plasma sintering. In cold pressing, you can see, and sintering, you can see there is a crack where the tungsten and copper layer, tungsten and copper gradient is more. The crack will form, and it will be cracked into two form. And in uniaxial pressing also, you can see there is a this is not a sinter, this is sintered. So upper part is not sintered, down part is sintered. So this is not suitable for this process. So we use spark plasma sintering. Here you can see that all the samples get sintered completely. If this is the copper side, tungsten side, you can see both are means all the layers are sintered. So here I have, this is the different density we have got during sintering, which using different temperatures, and this is the different layers of the XRD, which is showing the tungsten and copper. It is does not showing, is only the peak height difference, means where tungsten is high, you are getting high tungsten peak, and where copper is high, you are getting high copper peaks. This is actually all the layers you can see here. This is the here tungsten is higher, this is the copper higher. So you can see all layers are completely sintered in the spark plasma sintering. And this is the layers by the microscopy. This is the scanning electron microscopy image. You can see this is the 100% copper. This is tungsten copper. This is tungsten copper. Tungsten copper. Here we are increased the tungsten in this one. Here 100% tungsten, 80%, but 100% layer we have not shown here. So you can see that all the samples are completely sintered. Even you can see the higher image, high magnification images as well. The hardness of the layers are also checked, and you can see this is the copper layer, and this side is the tungsten layer. Here we have increased the tungsten, here 100% tungsten. So the strength wise also, or the hardness, you can see this is the lower hardness, higher, like that, this are increasing. So and after the hardness, you can also not get any layer difference in the delamination in the part of the layers. And then we have to check the final mechanical property, whether our composite is prepared, this functionally graded material is okay or not. So we have checked in the by compression testing. You can see that this is the samples and this is the loading directions, and you can see that different sintering temperature. These are the samples are 950, 1000, 1050 degree temperatures, and the 950 degree temperature you can see there is a cracks in the samples, and here you will not get any cracks, but due to loading the copper side is deforming. That is usual, where the material is a lowest yield stress of the copper, that's why it is deforming. Here all these, but cracks are forming in this one, so that's why we found that 1000 and 1050 degree temperature will be is better in the spark plasma sintering for this composite. So now I'm going to end here. So just to little summarize the talk, I can say that the lightweight metal matrix composites are a most prominent material, and it has a lot of usage in aerospace and automobile sectors, and day to come where when the automobile and the aerospace sectors, people will find that many parts are made from these composite materials, because it will be reduce the weight and it will increase the fuel efficiency of this aircraft and other vehicles of the automobile. So that's why there are a lot of research is going in this area, and the industry are very much keen to replace the high weight material with the low weight composite material to reduce the fuel, to increase the fuel efficiency of the vehicles. And it is also equally important for this composite material for engineering and other application, but cost-wise the production is high in case of composites. So this is one of the limitations where the composite are actually not getting much importance or much usage compared to the other simple material where both can perform. So the companies are mostly preferring to the single material, not a composite, where not a critical requirement. So that's why the some process has to be developed, or some continuous research is required to produce a composite where with a matching cost as per the single material. And also I have shown the case study of the three materials. This one, the aluminum magnesium composite, aluminum calcium composite, and this tungsten copper functionally graded composite, which shows that the composite can be successfully made as per the property requirement of the components, and the property can be tailored by the changing of the composition, temperature, and different other variables to get the required property. So with this, I thanks for your kind attention, and if any question, so kindly go ahead.
Thank you, sir, for a brief introductions. I mean, on this metal matrix composite. I think you have demonstrated it quite elaborately by taking 3 different case studies, and also the different case study for this SEM and XRT. I think the students, those who are working, or the professors, those who are working on this field, will definitely take the advantage from here. Thank you for your slide, sir. And now I request all the participants, those who wants to ask any question, can unmute themselves and ask the questions.
Hello, sir. Good afternoon. I'm Shweta Gantar. Sir, regarding nanoparticles, that they have high conductivity. My question is there any possibility that if we lower the temperature to absolute level, like absolute temperature, the nanoparticles start behaving like superconductors?
Yes, whatever I understand, you are telling that nanoparticles, when we are heating, it will become a micron size. So you want to decrease the sintering or your composite making temperature so that it will be remain in nano size? Yeah.
Yes, sir. Yeah. And if the
Yes.
conductivity, how would it affect the conductivity of it?
Last part I could not hear. Can you repeat just once again?
Yes, sir. Actually, my question is that if we reduce the would the nanoparticles start behaving like superconductors?
Nanoparticles are behaving like a superconductor, you are saying.
Yes, sir.
By reducing the size.
The temperature, sir, working temperature.
Yeah, there is a possibility. Actually, because the nano, if you are reducing the size of the particles, they are behaving different than the bulk form. So, if you have certain materials which have a high thermal the conductivity at the when you are going to reduce the size further and further and further, so there can be a critical size where it can be behave a superconductor. Yeah, there is a possibility.
Okay, sir. Thank you.
Thank you.
Any other questions from?
Excuse me, sir. This is Dr. Jitan Sahu. Good afternoon, sir.
Yeah, good afternoon.
My question is that if we are considering two material,
yes.
If you are considering two material which is having of different density, like
yes.
I had chosen aluminum and another one is your nanocarbon tube.
Yes.
So, how this can be mixed and composite form? How it can be done?
Yeah, very good question.
So how
yes.
it will be possible to mix up and to get a better composite material?
Yes, yes. Actually, the aluminum and carbon nanotubes we cannot mix easily because both having a high density difference. Aluminum is a higher density compared to the carbon nanotubes. So if you are mixing, just melting and putting the carbon nanotubes by stirring all these things, it will not mix completely. And somewhere there you will get agglomeration, somewhere it will be floated, and some you will get a different distribution of the reinforcement in the matrix. So in this way, there are 2-3 methods. Either you functionalize your CNT with this aluminum, and then you can mix with this aluminum matrix. Either you by say liquid stirring method, whatever you have to do, you melt the aluminum first and then put the CNT in this one and go to just to reduce the temperature below the melting point, so that your aluminum going to a semi-solid stage. So in that case, then you start stirring. So there will be actually not a complete liquid of the aluminum. It will be a semi-solid. So some mechanical interlocking will be there in the aluminum and CNT. So there again still will be some not will be uniform. But then again you increase the further temperature above just 20 to 30 degree melting above melting temperature. Then again you mix it, and then again cool to the semi-solid region, and then depends on your how much percentage of the CNT you want to mix it, because you cannot mix a higher percentage of CNT in this one, but lower percentage of CNT you can mix by this process, and then by means going above the melting temperature and fed again down this semi-solid region, and then again just melting and again casting it. So this way you can get a composite which is having a lower volume fraction of CNT. But if you want to increase further of the CNT in this one, then you have to go for one powder metallurgy process, where you take a aluminum powder and you take a CNT, mix it, and then mechanically mill it, so that you get a uniform mixture, and then you can sinter it by powder metallurgy process. So in that case, your CLT will not go here and here, will not agglomerate it.
Okay. Thank you.
Okay, one or two more questions can be taken. And so if anyone asks, you can ask.
Okay, thank you, sir, for your excellent presentation. Myself, Manila. I want three questions need to ask.
Yeah.
Sir, what is the advantages of cryomilling?
Cryomilling in certain cases very much advantageous, where you are, suppose if you are milling the ductile material. In ductile material, it is not by normal milling. You cannot go a size at a certain below certain size, and if you are milling a longer time, you get a more fine particle again agglomerated and become a bigger size. But if you are going for a cryomilling, so you whatever what you are doing, you are decreasing the temperature of your material below at the cryo temperature. So in that case, what happen? Your material ductile to brittle transition below your ductile to brittle transition temperature. So your material will not be a ductile at that cryomilling temperature. It become a brittle. And in the when material will become brittle, then it will be a fracture easily, so that you can get a fine powder very easily with a very low time. Even if you using a non-ductile material also at a cryomilling temperature, so you will where you need a 30-40 hours of milling, you can make a material in 1 hour or 2 hours in cryomilling. So then in that case also advantages. And in some case where you cannot reduce the size of the in normal room temperature milling of the material, so in that case you have to completely you have to means bound to go to the cryomilling condition. Otherwise you will not get your powder in the fine form, or if you want to go a nano size range.
Okay, thank you, sir. The next question is about your case study 1. In that case, you said that you had added 7.4% aluminum in magnesium.
Yes.
So, what was the reason behind that?
Actually, I think your mechanical background, your metallurgy somehow.
I'm from, sir, I think you have remembered myself, Manila Malik. From this.
Yes,
sir. I'm from metallurgy background.
Okay. Then so you know that magnesium phase diagram, magnesium and aluminium. So according to phase diagram, we can go up to maximum 10% of aluminium can be mixed at the temperature of the above 400 degree temperature. But if you are reducing the temperature again to room temperature, then some aluminium will come out from the magnesium, and less than 1% aluminium will be remain in the magnesium because of the solid change of solid solubility range.
Yes.
Diagram at a room temperature, we can have the aluminium in magnesium less than 1%, and we are adding 7.4% of aluminium. You are saying, but it is possible by powder metallurgy route. By liquid metallurgy route, phase diagram. Our phase diagram is designed for a liquid metallurgy route. So by liquid metallurgy route, whatever is possible, maximum 1%. But here we have done experiment, and we found that 7.4% is the optimum aluminium, maximum aluminium which we can add in the magnesium by this powder metallurgy route. So in that case, some aluminium is going in solid solution, and some aluminium forming intermetallic compound. But intermetallic, if we increase aluminium, suppose 10%, 12%, then intermetallic will be more. So intermetallic, we don't want to increase the intermetallic. Otherwise, intermetallic will form act as a stress razor, and material will crack during your different applications. So in that case, we have to optimize the 7.4%. In that case, some part is going solid solution, some part is forming intermetallic, and intermetallic again refines. So the size is so in the nano size range, so that it not act as a stress razor. It acts as a grain boundary strengthener. So it again increase the strength of the material. But if we are increasing the aluminum above that, then intermetallic will be more, and it will also not refine, and it segregate along the grain boundary, completely compact the grain boundary, and again the material failure become easy. So in this case, we have optimized it to 7.4% maximum, so that we can get a higher strength as well as to reduce the effect of intermetallic.
Okay, thank you, sir. So my third question is, you had one slide based on the particle size, effect of particle size. So
Yes.
how you have chosen that particle size? After milling, you did some you have done some sieving, or what?
Yes,
How you
yes.
decided the particle?
Yeah. Sieving. Suppose I have taken 100 to 80 micron in that range, plus minus 100 plus 80. So I take two sieve, 100 micron sieve and 80 micron sieve. So in between whatever above the 80 micron sieve and below the 100 micron sieve, that is the range of the particle of the size plus minus 100 plus 80. And suppose 80 to 40 range, 80 to 40 means 80 micron size sieve and 40 micron sieve. So in between that one is 80 to 40 micron. Minus 20 means whatever last part, minus 20 is very fine, whatever is there. Minus 40, 20 means it may be minus 20, it may be minus 10, minus 1, whatever will be. So by this sieving, we have segregated the different particle size range.
Okay, sir. Thank you, sir. Thank you.
Okay, thank you, Manika.
Thank you, madam, for asking questions and participating in a more friendly way.
Hello.
So I request any other participant to ask any questions. So if no more questions, then we can stop this question and answer session. And thank you, sir, for participating here. And now I to address this.
Thank you, Sandeep. Hello, if no more questions, so then Mr. Sandeep, so I can now thank you for giving this chance to present my work in front of your this audience. So now I can disconnect.
Thank you, Dr. Chobeji.
Yes, sir. Thank you.
Thank you. I'm principal speaking. So thanks a lot for giving your time, valuable time, and address the students and also the research scholars and faculties, and enlighten them in the field of composite material, what experience you are bearing. Thanks for that, sir.
Thank you, sir. Thank you for giving this opportunity to present my work. So I think most of the people have got some advantage of this.
So later on, we'll be in touch with you for student internship and other type of things. If anybody interested to work, because so many students they have participated this time in this webinar. If somebody wants to work that area, I will take your help, sir.
Yes, sure, sir. Even this year, this COVID problem, we could not actually able to take the student and physically come over and work here. But CSR has find out one scheme so that by webinar we are taking the students. Suppose in our institute there is a 40 to 50 students have joined by webinar series. We are giving some work through webinar and giving some research and some topics we are talking, and some giving some questions to them, and they will do it by this way.
Nice, sir. This time, deputy in the curriculum they made the project or internship for 6 months, that entire 8 semester. So from January to April. So in during that period, if any students want to work with you, they can directly approach you through us, and we can think of. They can go to you for 4 months to work with you if you have any problem for that.
Yes, sir. We have different projects we are working on different, and the student can take a benefit of that. But before that, actually, they can directly contact to scientists.
So the formality, whatever is there for IMT, we have to fulfill that. If that is the things we have to do. That part.
Yes, sir.
We have to
Yes,
go
sir.
for that, sir.
Yes, sir. Yes.
Okay, sir. Thank you, sir.
Thank you so
Okay.
much, sir.
Thank you, sir.
Thank you so much.
Thank you, Kanchan. Thank you.
Thank you, sir. Thank you.
Thank you, Mr. Sandeep.
Actually, one more announcement will be there for the participant. And in the chat box, there is a feedback form. All the participants are requested to fill that feedback form. And thank you all for participants to participate here in this webinar. Thank you, Principal Sir. And thank you, HOD Sir. Thank you, SPIU Head Antaryami Sir, for providing such a platform for all the participants to get a good knowledge, sound knowledge on all this composite material, polymer composite as well as our metal matrix composite. I hope all the participants will be benefited out of this webinar. And thank you for participating, all of you, in a nice way. I hope it's a nice presentation. Both of the professors have presented elaborately on all these things. So I hope you have some benefits out of this webinar. Thank you all. Thank you, sir.
Thank you all.
Yes, sir. Thank you, sir.
Thank you both the coordinators for their coordinated effort to make this program first webinar of the college in this
Yes,
COVID
sir.
period.
Thank you, sir, for your support.
Okay. So finally, I thanks all the participants. Those during this COVID period, they have participated and or take part in this webinar of the PMEC for the first webinar of mechanical. So thank you all.
Yes, sir.
Now, madam, it's your turn.
Yes,
So to close the function. Okay.
Yes,
to
sir.
close the webinar. Thank you.
Thanks to all the participants who have joined prior to the meeting, and thank you all for your support. And we in near future we are going to organize one more FDP and one more seminar. I'm also sending the link within some few days. Please join that also. Thank you so much.
Kanchan madam, one thing from my side, we can think of a latest machining. On machining, we can have a webinar as early as possible.
Sir. Yes, sir. We will discuss, sir.
As early as possible.
Participants, if any questions regarding any feedback form or anything else, please let me know. Before that, hello.
Madam, I am quitting.
Yes, sir. Yes, sir. Yes, sir.
Thank you.
Sir.
Thank you.
Hello. Yes, sir. Yes, sir.
Hello. Madam, good afternoon. Hello.
Yes, sir. Yes, sir. Please.
Yeah, madam, good afternoon. I am Satyabrata Jana calling from Hyderabad.
Yes, sir.
Am I audible?
It's audible, sir.
Madam, regarding your future FDP and webinar, add it in the group only.
Sir, just
hello.
Sir, actually we are having your email IDs. We will let you know, sir.
Okay.
Right
Thank you.
Now,
Thank you very much.
the thing is that we actually in the month of March it was planned, but due to this situation we have to cancel that. It was on March 28-29. So we are planning to do that in online again. So we all are having your mail IDs and phone number also in the group. We are not going to cancel this group. In the group itself, we will send.
Okay.
Is it okay?
Okay.
Okay, sir.
Thank you very much.
Sir, have you filled the feedback form?
Yeah, just not going to be.
Please do it and let me know if any problem in the certificate.
Okay. Thank you very much.
Okay, sir. Sandeep, sir?
Yes, ma'am. It is, I think, yes. It is in the chat box, the feedback form is there. Once again, all the participants are requested to fill the feedback form, so that once you all get the feedback form, then we can wind up the sessions. or if anyone else still left, then you can write to us, or for Kanchan madam and for me also. Both the mail IDs mentioned in that mail that is sent to you. And also thank you once again, all of you. Thank you, madam, for cooperating all these things. And now we can, I think, wind up the session.
Okay, thanks.
Thank you.